why would they let someone that plays that and thinks that's funny teach? So, all right. So let's get into it. So we're going to start off with just a quick little, another little comic, again, lighten the mood a little bit. Because again, we're talking about a not so fun topic today where we have this little gentleman. I pulled this off the internet so many years ago, but he's in his car. He's looking at his rear view mirror, object mirror are closer than they appear. And in his rear view mirror, he sees global warming running at him and this guy with an oblong head and is very, very bald. And I think this comic, in addition to the little cartoon from Futurama, highlights another key aspect of climate change and global warming as a process is that the effects of it are really closer than we think. It was really sort of when it came to the spotlight in the 90s, it was this far off problem, right? It was a problem of the 2030s and the 2040s and the 2050s, but those time periods are right around the corner. So it really is closer than it appears. So we're going to start local because when I talk about climate change, and it doesn't really matter who it is, I like to start local. And local means Massachusetts. And so Bentley's in the greater Boston area. So I have these two pictures, one of which is mine and one of which I just pulled off the internet. And now this picture is taken in the Boston area. Does anybody recognize maybe this landscape or maybe this castle-looking thing with all the weather instruments on it? Yep, Megan?
Okay, now that I'm looking at it, I think this might be wrong, but that's not the Quabbin Reservoir, is it?
Nope, that's a little too far out, but good guess. This is actually pretty dang close to Boston. So it's in one of the surrounding towns of Boston. And I don't mean like Hyde Park or anything like that. I mean like one of the towns, or one of the many towns, I should say. Yep, Karina?
Is it Blue Hill?
It is Blue Hills. And so this is Big Blue. This is the Blue Hills Observatory on top of Big Blue Hill. It's not a particularly fantastic hike. It's like 580 feet. So it's an easy thing to do if you're not a great hiker. So if you've never been to the Blue Hills, it's this really nice reservation just south of Boston in Quincy, Milton, Randolph, and I think Braintree too. Might be Braintree, but I definitely know it's those three towns. Now, they're just a bunch of hills, because they're called Blue Hills, obviously. And on top of the biggest hill, there's a weather observatory. And this weather observatory has been going since the 1850s, which it probably explains why it looks like it's a castle, back then architecture, right? So we have this cool nature preserve in the middle of the greater Boston area. It's kind of like the Fells, right? This really nice area. And we have this weather observatory on the top of the biggest hill. And so this is just a temperature record. Now let me orient you to this graph. We have temperatures in degrees centigrade here on the left for those that are not on the imperial system and for those of us that are used to seeing degrees centigrade. And then we have degrees Fahrenheit for everyone else that is not super familiar with degrees centigrade here on the other y-axis. And then we have the time, so the 1820s all the way up to last year, or actually the year before, because they only, 2 years before, I should say, in 2017. And the red line is the 10-year mean, and the red line is the 30-year mean, and the blue line is the 10-year mean. So, and I should also mention the black line are the yearly recordings. So these are the actual real-time recordings of the observatory of just temperature. So, what do you see? What do you see? Yep. Aramis?
An average rise in temperature since 1820.
Yep. So that's the first thing. Yeah, an average rise in temperature since the 1800s. All three lines are going up and up and up, right? It's going up by, started at 7.5 or so, and by the turn of, about the 2020s, it's up to 10. So we're seeing a pretty substantial rise in temperature in the Blue Hills Observatory over time. Cool. Does anybody notice any other patterns? There's only one other pattern I'd like to point out about this graph. But you nailed the nail on the head with rising temperature. Well, this one, you want to look at the black line. And the black line is pretty interesting, where you see, we'll just start at the tail end here, or maybe actually it's better to start here in a more contemporary time. You start off here around 9 degrees, and then within a few years, you're up to 10 degrees, and then you're kind of back down to 9 degrees again. So you see this pretty dramatic shift in temperature annual temperature, of course, in a yearly period. And so the other key takeaway from this graph is that while temperatures are increasing, there is a significant amount of year-to-year variability, but the overall trend we observe at the Blue Hills Observatory or any other observatory that's monitoring temperature on the planet is a steady rise in global temperatures starting after the 1820s. And as we discussed, the 1820s is really when the Anthropocene kicked off in full drive, right? This is the Industrial Revolution, right? When we started combusting coal, oil, and eventually natural gas, leading to this pattern that we're seeing. So keep this in the back of your mind. This is local. If you're from the Boston area, this is what's happening in the Boston area, but it actually doesn't really matter where you go. You can go to Hawaii, you can go to New York City, you can go to Dubai, you can go to Madrid. It doesn't matter where you go. The pattern is the same, increasing global temperatures, which I think is a sort of a remarkable thing when you sort of think about it, that there's a pattern that's happening globally, but a scary pattern nonetheless. So our agenda for today is multifold. So we're going to talk about the distinguishing features between climate and weather. We've discussed it a little bit. We're going to dive a little bit more. Then we're going to re-dive back into the atmosphere, talk about it in much more depth, in particular, talking much more thoroughly about our friends, the greenhouse gases, and how it influences warming on the planet. Then we're going to take a deep dive into an 800,000-year look at Earth's climate, which I think is an exciting thing. Then we're going to look at how humans factor into this climate crisis that we're currently in. And then we're going to look at impacts of climate change on now and what we project to happen in the future. And we're going to spend a little bit of time focusing on what we call climate feedback loops, which are probably the most damning feature about climate change. And then I'll end with some anecdotes about climate change, you know, what can be done and those sorts of things. So let's get into it. So climate versus weather is really two sides of the same coin. Right? Weather is what's happening right now. So when I woke up this morning, I looked at my phone. My phone told me it was going to be about 80 degrees today in where I lived and sunny. So that's the weather, right? What is the wind, the humidity, precipitation, solar input, temperatures, cloudiness, any weather-related phenomena that you can think of, that's our weather. And it's short periods of time, hours. You know, you guys probably all know that, you know, weather can change relatively rapidly, right? It could be cloudy 1 minute and then pouring rain the next and then beautiful and sunny the next, right? So weather is short time periods up to weeks long, but our climate, while it encompasses weather as a concept, it is extended over large periods of time, and we're thinking years to decades. So when we looked at this graph of the Blue Hills, weather is the black line, climate is the 10 and 30-year averages. But you'll notice they line up pretty well. Right? Not just the averages, but the trends of the black and the trends of the red and the trends of the blue line up pretty well. So climate is when you turn on the Weather Channel, when you open your iPhone and you pop open the weather app, that's what's happening in your neck of the woods, as Al Roker used to say on the morning news, or he still says, I guess he still does his own thing. And then we think of climate is when we think about long-term patterns. What is the weather like in Massachusetts like today, 10 years ago? How does it change over the 10 years? That's what we really think about as climate. And so clearly this is the weather, this is the climate. So this leads us back to the atmosphere. Remember, the atmosphere is relatively short, right? You could hop into a car, drive vertically at 60 miles an hour, and you would escape our atmosphere within a single hour. It is not very large, but remember, the atmosphere is very, very important to not just weather, but also to climate and the way sort of the Earth functions as a whole. Now, remember, most of our what we care about is concentrated in the troposphere, so that lower area of the atmosphere. So basically the first 10 kilometers, that's basically where all weather does occur. And when we think about sort of climate change as an effect, it's mostly affecting this area of the atmosphere, though it certainly does affect all aspects of our atmosphere. Now, the atmosphere itself is comprised of very few gases, which I think is a pretty remarkable thing. Now, the modern atmosphere, and the atmosphere has changed considerably over time. Sorry if you can hear my dog barking. There's someone at my door. Today's atmosphere is remarkably simple. Now it's about 78% nitrogen. Now this nitrogen, it just hangs around. It doesn't do anything. You breathe it in all the time, but it doesn't affect you. It doesn't affect climate or anything like that. It's just kind of hanging around. Then we have arguably the most important gas, which is oxygen. Now, this is something that you rely on every day, oxygen being at about 21% of our atmosphere. And clearly a very, very important gas. You breathe it every day, right? It's vital for life. So that's 99% of our atmosphere, just those two gases. Now, the remaining 1% comes down to a few different gases. Now, carbon dioxide is one of the other big ones, but we also see other gases such as argon, or argon, I should say. Water vapor is pretty dang important. But again, most of our atmosphere is comprised of just two simple gases. Now, these gases that comprise that less than 1% will actually become relatively important in a few slides when we start talking about their effects on their climate, on our climate, I should say. Now, as we mentioned in the previous class, there is the ozone layer, and I forgot to make mention of it. This little thin layer here in the stratosphere. This is the ozone layer. Now, the ozone, it's defined as 3 molecules of oxygen bound together. It's arguably the second most important gas in the atmosphere. And as we mentioned, the ozone layer, as this graphic depicts, blocks ultraviolet light. Now, ultraviolet light is mutagenic. It will damage your DNA. So the ozone layer is a really important thing for helping life survive on this planet. Without the ozone layer, we would be toast. Right? We couldn't live on land. We could only live in the water, but clearly we live on land. So clearly the ozone layer plays a really important role in your average everyday life. And in particular, if you're like me and you're a pale person, you love the ozone layer because it keeps you from getting severely burned. Now, the ozone layer has, like many parts of our lives, been affected by human activities. Now, in particular, there's a couple gases out there. They're called CFCs, or chlorofluorocarbons. We'll talk about them shortly. These gases, which were actually typically used in refrigeration materials, so air conditioners, our commercial and industrial freezers and fridges, they were great for cooling. But once they would make it out into the atmosphere, these actually CFCs would react with ozone and destroy ozone, making our ozone layer very, very thin. So as such, scientists recognized a problem, and we globally convened what was called the Montreal Protocol in 1987. So, long before you guys were all born, actually even before I was born, a year before I was born for that matter. The Montreal Protocol was actually a really successful thing. If you want to read about it, you can certainly click this really nice article here, or there's 2 links down here for you to take a peek at. But it did aim to tackle this problem by actually banning the use of CFCs globally. And so it was this really great treaty. And actually, you can sort of see your ozone layer really, really red here in the 90s, recovered quite well into the 2000s. And the hole is actually pretty got really, really small at one point. But as we'll discuss later in the lecture, it's actually starting to make a resurgence, the hole in the ozone layer, due to one specific gas that we'll spend a decent amount of time talking about. So don't forget about the ozone layer. We're going to come back to it in pretty shortly, I should say. But again, a really great piece of international policy that tackled a problem that was a global problem and fixed a global problem for a short period of time. So remember the Montreal Protocol when anyone says that we're doomed, right? Because the Montreal Protocol was effective, it worked, and it was universally adopted. And so we can fix problems at the global level. We just have to follow the protocols we set in place. So the final thing I'll say about the ozone layer is that ozone depletion, or ozone as a gas, actually does not affect climate change or cause climate change in one bit. Now, the most common type of radiation that warms our planet is what we call essentially thermal radiation from the sun. And so that thermal radiation, which warms our planet, is not affected by ozone in the slightest. And so while ozone does absorb ultraviolet light, it doesn't absorb the important warming rays of the thermal radiation. And more importantly, UV light plays a minute role in climate as a whole. So I bring this up specifically because a lot of times where you see people talking about why climate change is not bad or anything like that, they'll oftentimes talk about ozone depletion as being a bad thing and it's simply just not the case. Ozone just does not play a large role in our climate change that we're seeing right now. So it's an important thing for sort of the overall discussion. So this gets us to the topic we're going to spend a few slides on. Now, it comes down to one question, and this question can be answered in either one or two words. So I'll pose this to you guys. You can answer in the chat. You can answer it just by speaking. How is the Earth warmed? It's a one-word answer or a two-word answer, depending on how you want to say it. So what do you guys think? How is the Earth warmed? Let's see who answered first. So Karina gets the brownie points for the day. The answer is sun. Yes, the sun. So you're jumping the gun, Nicholas. That's true. We'll get to that aspect. But the ultimate heater of the planet is the sun. If there wasn't a sun, our planet would be cold. Right? That's just simply the reality of it. Take away the sun, all life dies. Earth becomes one giant snowball. So the Earth is warmed by the sun. But as Nicholas pointed out, it's a little bit more nuanced than that. Right? While the sun is the driver of everything on this planet, there's a few other factors that influence how the Earth is warmed. So let's talk about the first one. Now, it's called albedo. This is how you spell it, albedo. So I think it's kind of a fun word to say, at least in my opinion. But it simply refers to how reflective the Earth's surface is. Now, to give you an example of how this works, I'll talk about something we all know and maybe not love, but we all certainly know of. Now, if you have a car, and say you're like me and you have a black car, and then say you have a friend potentially like me that has a white car, and you both drive to the same parking lot, say you're going to Target together or whatever. You park right next to each other on a hot summer day in Massachusetts. You go and shop for an hour at Target. You buy all sorts of things because, Target has everything. And then you come back and you get into your car and your car is sweltering hot. It is so hot, like you feel like you're going to pass out. So you get out of your car right away and you see your friend hop into their car next to you and they're just kind of chilling. It's a little warm for them, but it's not as deathly hot as your car is. So what the heck's going on with that? Well, that's albedo at work. The dark car absorbs more solar light, so energy from the sun, thus warming the car faster and making the car overall hotter. Whereas the white car absorbs less of that light. It reflects most of the light back away from the car, thus keeping the car overall cooler. So if you ever wonder why cars are differently hot depending on their color, or if you ever wonder why I'd say asphalt gets scorching hot during the summer. So if for instance, for those of you that have pets, asphalt, when it's about 80 degrees out, can well hit over 120 degrees Fahrenheit. So black, dark surfaces absorb a lot of heat. Light surfaces reflect that. And that's the albedo. And the Earth's surface is very much like that. And we can just look at this simple diagram where we have snow covered or ice covered, whatever you want to call it. The sun's radiation hits. Only about 10 to 15% of the sun's energy is absorbed, while the rest of it is reflected right back into outer space, thus keeping the snow overall cooler. Similarly, we can look at this dark surface of, say, soil, where 70% is absorbed. We can look at slightly less darker forest, where 80% is absorbed. And then we could see that, lakes and surfaces of water, they reflect a decent amount back as well and absorb a lot of energy as well. So darker surfaces mean a warmer planet. And if our entire planet was black, for instance, just somehow it was just all black basalt rock or something like that, our planet would be scorching hot because of the albedo. However, if our planet was covered in ice, it would be nice and cool. Obviously because of the ice, but the albedo would continuously make it cool. So that's the albedo. That's one part of how the planet is warmed, the reflectivity. Now we'll talk about this idea of reflectivity later in the class when we talk about climate loop feedbacks, but keep it in the back of your mind. Think about how the albedo might change with the things we're going to talk about. Now, the other part of climate, and I should say how the planet is warmed, is actually what we term the greenhouse effect. Now, the greenhouse effect actually as a concept dates actually back to the 1920s in that ballpark. So it's been around as a concept for 100 years. But, and actually kind of funny enough, scientists back in the 1920s, if you read some of their research, were actually warning people through their research that climate change, like man-made climate change, could actually be a meaningful thing going forward, which is kind of a crazy thing to think about. how big that discord is nowadays versus like, hey, here's this anecdotal thing that might happen that they put back in the 20s. But that's just a little history lesson for you about the history of the greenhouse effect. But you guys all probably have heard of the greenhouse effect. It picked up a lot of steam in the 90s as a concept. So let's dive into what the greenhouse effect is. And it's called the greenhouse effect because it's really the planet, because of the gases in our atmosphere, basically acts like a greenhouse. And so for those of you that ever been into a greenhouse in the middle of winter, the greenhouses are pretty warm in the winter. Now, why is that? Well, the greenhouses, they're all a bunch of glass, but the glass is very, very thick. And so sunlight comes into the greenhouse relatively easily. And it when it bounces off the surfaces in the greenhouse and it tries to leave the greenhouse, it actually gets trapped in by the greenhouse's glass. It's kind of a cool glass. And so just as a note, so it's really cool like physics behind it if you want to Google it. But the idea being is that the radiation comes into the greenhouse. Some of it can escape the glass. It's very, very hard, but some of it does. But the rest of it's just trapped in the greenhouse, thus warming the greenhouse. And that's what's happening in our atmosphere. We have a number of gases, and we'll talk about those gases in depth in just a moment. But carbon dioxide, water vapor, methane, nitrous oxide, chlorofluorocarbons, all these gases act as essentially the glass on a greenhouse, trapping solar radiation. So let's just sort of conceptualize this. We have the Earth. It's chilling in the middle of space, rotating around the sun. The sun's radiations come in. It hits the Earth's surface. Depending on the albedo of the Earth, it reflects some of that back up into the atmosphere. Some of it makes it into space, as you can see, but other are trapped by our atmosphere, greenhouse gases, reflecting that solar radiation back down to the planet, thus warming our planet. Now, the greenhouse effect gets a lot of flack as like a fear-mongering thing of climate change skeptics or things like that. But the reality is the greenhouse effect is just a natural phenomenon. It just happens to play a central role in human-induced climate change. So we're going to do a cool little thought exercise that I like to do. And the greenhouse effect is natural. Now, I'm going to ask you guys what you guys think the answers to do. And if you've looked at the slides ahead of time, please don't answer. Let people who haven't looked at the slides try to answer this question. Now, what do you guys think the mean global temperature would be with greenhouse gases? And what do you think the mean global temperature would be without greenhouse gases? So with the greenhouse effect, without the greenhouse effect, what do you guys think? And there's no wrong answers here because you're just guessing, right? What do you guys think? No one wants to take a stab? One brave person. With greenhouse gas is 60. Is that Fahrenheit, I'm assuming? I'm just kidding. Of course, it's Fahrenheit. It would be blistering hot if it was 60 degrees centigrade. Yep. So you're actually right on the money. The mean temperature with greenhouse gases is about 60 degrees Fahrenheit. Now, what is it if we got rid of all of our beloved greenhouse gases? What would the temperature be? And it might shock you. So that should tell you should aim. Ooh, minus 20, that's a brisk temperature. That's a little bit too cold, but good guess. You're heading in the right direction. So it's warmer than minus 20, but colder than 60. So where are we at? 55. Samantha's not a big fan of our greenhouse gases. She thinks they're no good. Megan's getting closer at 15. I'm just saying, Samantha, you said they warmed by 5 degrees. So it just sounds like you don't like greenhouse gases. So 15 is the closest answer thus far. Anyone else want to toss their hat in the ring? 20, that's still a little warm. Nicholas is the closest. Megan, you're still pretty close. So I'm gonna, yep, spot on. Yep, Nicholas got it. So it's 0. So with greenhouse gases, so the way our Earth is right now, the mean global temperature is about 59 degrees Fahrenheit. If you stripped away all greenhouse gases, all of them, our temperature of our planet would be 0 degrees Fahrenheit, which you guys probably know the freezing point of water is 32 degrees Fahrenheit. So we would be minus 32 degrees here on the planet Earth. Fahrenheit, of course. It's like minus 15 Celsius in that ballpark. So cold, right? Was anybody surprised by that difference? A 60-degree effect. 60 degrees just by some gases that comprise less than 1% of our atmosphere having a strong effect. I remember the first time I learned this when I was, I don't even remember how old at this point, a long time ago when you guys were little, which I hate saying, but it's the truth. I remember just being astounded by this. Like, it is such a strong effect. Just a bunch of things you can't see have such a dramatic effect on the planet. So the greenhouse effect is natural, right? But the reality is, just because something's natural doesn't mean it can't be detrimental to the planet. So this is really where humans come in, right? When humans come in and we change how much greenhouse gases in the atmosphere, that's when things start to go awry. So let's talk about our greenhouse gases. They're really important. Remember, they are very rare, generally speaking, right? They're less than 1%. And they're comprised of a couple different gases. Now, the most common is water vapor. So just gaseous water. So if you guys have ever boiled water, you've seen the steam coming off boiling water. That's just water vapor. That's what helps make clouds and all that stuff. Water vapor is relatively short-lived in the atmosphere, just as a note. So we'll get back to water vapor shortly. Now, the other most common greenhouse gas is CO2, carbon dioxide. You guys have all heard of this one. This is the one that we're we're the most concerned about. And then there's some other gases, right? They comprise about 1.4% of greenhouse gases in our atmosphere. But again, CO2 is the biggest contributor to the greenhouse effect globally. So it is clearly the most important greenhouse gas. Now, you might say water vapor is more important, and you would be right. But we'll discuss water vapor in just a few slides and why it's the least concerning of all the greenhouse gases out there. But remember, more of these greenhouse gases in the atmosphere, more trapped heat, so the greenhouse effect increases, leading to a warmer planet. So let's do another little thought exercise here, where we have 3 planets, so our 2 closest neighbors, and Earth right here in the center. Now you see Earth, it's got 0.03% of its atmosphere is CO2. So it's very, very little CO2. We know the average temperature of Earth is about 60 degrees Fahrenheit in that ballpark. Then we have our friend Venus, our really, really hot neighbor closer to the sun than us. Its atmosphere is about 96% CO2. And then we have Mars, where our beloved Curiosity rover is hanging out, taking pictures, doing cool science for us. And it basically has 0 carbon dioxide in its atmosphere. All of its CO2 is actually trapped in the ground. So basically their atmosphere has 0% CO2 over there in Mars. So given the fact that more CO2 or more greenhouse gases means a warmer planet, what temperature do you guys predict that Mars should be? And what temperature do you think Venus should be? Just throw out guesses. But remember, Earth is about 60 degrees Fahrenheit. So what do you guys think? Anybody have any thoughts? We'll start with Mars. What temperature do you think Mars is? Temperature is Mars. Fun fact, a couple of years ago, I was in Montreal for New Year's, about 8 or 9 years ago. And it was colder in Montreal, Canada, than it was on the surface of Mars at one point. So kind of a fun fact there. But how cold do you think Mars is? No CO2 in the atmosphere at all. Basically no greenhouse gases, no water vapor, none of it. Minus 60, minus 10. I think those are pretty good guesses. Anyone else? Minus 70. I'm not going to give the answer away right now. I'm going to wait till I can reveal all of them at the same time. So we got a couple good guesses, but the trend here is cold, very, very cold. Minus 10, minus 60, minus 70. That's blistering cold. So good. I think those are good guesses. Now, what about Venus? 96% of its atmosphere is carbon dioxide. So how hot is Venus? What do you guys think? Venus, the god of love. 500, 120. I like Megan's guess. It's a hot. So you guys are going up, which is good. I'm glad you're going up. It's always a good thing. 120, 500. I like those guesses. So let's review what we got here. So the mean temperature of Earth is about 15 degrees centigrade. the average temperature of Mars is actually minus 50 centigrade. And our friend Venus has a mean temperature of 420 degrees centigrade. So remember, the freezing point of water is 0 degrees centigrade. So this is 50 below zero on Mars. It's blistering cold. Earth, plus 15 degrees centigrade. And our friends at Venus sit at 420 degrees centigrade. And the reality is that is 4 times the boiling point of water. 420 degrees is 4 times the boiling point of water. So you're talking close to 800 degrees Fahrenheit. So you might ask yourself, why did I show you this? The reality is it's just a great example. What does more greenhouse gases mean? No greenhouse gases means a blistering cold planet. A little bit of greenhouse gases means a habitable planet. Too much greenhouse gas means you live in a pressure cooker. So greenhouse gases are super important, but their balance in the atmosphere really dictates how warm your planet can physically be. So I hope you guys like those 2 examples. I think they're fun little examples, little thought exercises about what CO2 and other greenhouse gases play a role in our atmosphere. Now, let's talk about these greenhouse gases. Who are they? Now we have water vapor, just water. Now, it's just evaporated water from the ocean, from lakes, from your body, wherever water exists, which is pretty much everywhere. Now, it's an important thing to note about water. While yes, it is a very important greenhouse gas, it is directly tied to temperature. So what does that mean? Well, think about when you have a bottle of water on a really hot day in your car. You leave that bottle in your car, the bottle warms up. And when you come back after, say, an hour, you see a bunch of water on the roof of your bottle. What happened there? Well, the water warmed up, it evaporated, came up into the hang around and condensed on the top of your bottle. And that's what's happening in your atmosphere. A warmer planet means more water vapor. So water vapor doesn't really drive like warmer temperatures. Warmer temperatures drive a lot of water vapor. So that's an important distinction to make about water vapor. It's important, but it's driven by warmer temperatures. Then we have carbon dioxide. Now, carbon dioxide has lots and lots of anthropogenic sources, and we'll touch upon those later. But carbon dioxide naturally gets into our atmosphere by the decay of living material. Now, what does that mean? Well, if I have a sandwich and I throw that sandwich out because I didn't want it for whatever reason, which I would never do because I'm a big sandwich guy, but if I did, that sandwich would decompose. As that sandwich decomposes, it would release carbon dioxide into the atmosphere because all the microorganisms are releasing carbon dioxide. So that's how carbon dioxide gets to the atmosphere naturally, just organisms eating things. So carbon dioxide has lots and lots of natural sources. Plants produce carbon dioxide, we produce carbon dioxide, microbes, everything produces carbon dioxide. So there's lots of natural ones. We'll talk about the unnatural ones in a few moments. We have methane. Methane has one source in the entire natural environment, and it's actually from microscopic organisms. So there's a group of microorganisms. They're called methanogens. Their metabolism actually produces a little bit of methane. And so that's how we naturally get methane. There's no other natural source of methane outside of these microbes because while there is methane, say, trapped deep down, it simply would not make it to the atmosphere naturally if humans weren't involved. So I don't really consider that to be a natural source of methane, even though it technically is. Then we have nitrous oxide, which is my favorite gas. I studied this gas pretty intensely when I was a graduate student. It's a really, really important gas, what we'll talk about, but it does have a single, well, actually there's 2 natural sources, I should say. The first one is actually just from microscopic organisms, both in the ocean and in our soils, and also our agricultural soils, and we'll talk about that shortly. But we actually know that nitrous oxide as a greenhouse gas can be naturally produced by lightning. So every time there's lightning, the lightning puts so much energy into the atmosphere, it produces a little bit of nitrous oxide. So 2 cool natural sources of nitrous oxide, microbes and lightning. Sounds like a fantastic pairing if I do say so myself. And then our final one are what we call our chlorinated and fluorinated gases. So these are CFCs and FFCs. These are strictly produced by humans. So these are our main players of our greenhouse gases. There are some other ones out there that I'll mention shortly. but these are the most important ones, with carbon dioxide being the single most important greenhouse gas. So this is we have a little handy dandy table here for you. We have the greenhouse gases here. So we've talked about these three. We talked about chlorofluorocarbons, and we have a couple other gases that are much, much rarer, including hydrofluorocarbons, or HFCs, sulfur hexafluoride, which is actually used as an electrical insulator. And then we have nitrogen trifluoride, which is essentially an etchant for electronics. It's a gas they use to make tiny holes in electronics for circuits and all that engineering garbage out there. So these are our gases. This is their chemical formula, and this is their global warming potential. Now, what does that mean? Well, this is how much they heat the Earth on a 100-year time period relative to carbon dioxide. So carbon dioxide is kind of the gold standard, and we compare everything to carbon dioxide. And we see carbon dioxide has a global warming potential of 1 over a 100-year period. And it hangs around in the atmosphere for about 100 years. And then we look at methane. It's got about a 25 times warming potential than CO2. Then we look at nitrous oxide, gets even higher at close to 270. And then we start going kind of off the rails here when we get to these synthetic man-made gases, 10,000, 12,000, 23,000 times stronger warming potential than CO2. So these gases differentially affect the atmosphere's warming potential, but they also hang around in the atmosphere for different amounts of times. Methane is short-lived, but all these other gases have hundreds or sometimes even a 3,000-year lifespan in the atmosphere. So greenhouse gases, while they're important, but they have different effects on our atmosphere, different warming potentials, both in the short term and in the long term. So, but remember, in terms of the most important, our boy here, CO2, is by far the most important. So that's our atmosphere. That's how it's warm. That's our greenhouse gases. Does anybody have any questions thus far? It's kind of a lot of information. There's always so much to talk about with climate change, just to let you know. But does anybody have any questions thus far? Because we're going to take a deep dive into some cool data by looking at ice. I don't know how closely you guys pay attention to the news, but ice cores recently made the news because some scientists in, I think, Russia, if I'm not mistaken, were actually found some brand new viruses trapped in ice cores, very, very deep down. It's kind of a cool thing. All right, so if nobody has any questions, we're going to take an 800,000-year look at the Earth's climate, and we're actually going to do it by looking at Arctic and Antarctic sea ice cores. And so ice cores are cool. You can sort of see what this looks like. They have this really long cable in this tower. They have this drill that basically, you can see the drill bit here. It basically drills down very, very deeply, sometimes kilometers deep, into this ice. And the cool thing about ice, and it's actually similar to soil, the deeper you go in ice, the older the ice gets. Now, the reason we care about ice is actually the way ice forms is it just snow falls. The snow melts when it hits the ground, and then it freezes back into ice. So when water freezes, and you guys have probably seen this when you've made ice cubes, when water freezes back into ice, it traps gases in the water. I'm sorry, in the ice. So whatever gases are found in the water and found in the atmosphere get trapped in ice. So our ice cores actually have a perfect preservation of the atmospheric concentrations of gases at the time when they freeze. And so the idea here is if we can trap the atmosphere's concentration of CO2 and methane and oxygen over time, and the deeper we go, the older we get, we can use these ice cores to reconstruct Earth's atmosphere back in time. And so the other analogy I'll just sort of give you, if anything I just said was unclear, it's like rings of a tree, right? You can look at rings of a tree and how many they are to understand how old the tree is. And you can look at how wide the tree rings are to understand how good the growing season was for a tree. It's kind of like our ice, right? It tells the sort of different layers of ice tell us a lot about the past. So now when we look at these ice cores, we look at a couple things. The first is we actually just looked at the gases that are trapped. And so we can look at CO2, methane, nitrous oxide, whatever is there, we can find, we can analyze, and we can learn its concentration in the atmosphere. The other thing we look at is actually what we call oxygen isotopes. We won't really get into how this works, but just to know, we can reconstruct temperature by looking at oxygen isotopes. And if you want to know more about that, you can bug me after class. It's just kind of beyond the point for this little spiel. But that's how we figure out temperature, and that's how we figure out the atmospheric composition. So let's look at the data. So we have CO2 in parts per million. Now remember, when we say something is parts per million, if I had a million jelly beans and one of them was red and the other 999,999 were green, my parts per million would be one red jelly bean parts per million of jelly beans. So that's what parts per million means. And we see 800,000 years ago on the left on both these graphs, modern times-ish here on the far right at 0. And we have CO2 at the top and Antarctic temperature at the bottom. So what patterns do you guys see, if any? And it could be N1, they could be together. Yep, what do you see?
With a rise in CO2 parts per million, the temperature also rises.
Good, yeah, so that's one of the things that I would hope someone would pick up. But yeah, as CO2 changes, temperature changes as well. And I think this was really highlighted in a couple spots. We can see right here, CO2 goes up, temperature follows. CO2 goes up, temperature follows. CO2 goes up, temperature follows. And the remarkable thing about this is they track pretty consistently over this 800,000 year period. So before humans even existed. And the cool thing, and I should put this graph here, but you can plot this. So you could put CO2 on the x-axis and temperature on the y-axis, and they actually have almost a perfect correlation. It's like, for those of you that statistics, it has like an R-squared value of 0.92 or something like that. So it's a really, really strong correlation. So when CO2 changes, temperature follows shortly thereafter. So that's an important thing, that we know the greenhouse gases are important, but there is a strong linkage between how much CO2 there is and what our temperature is. And it's not just modern times, it's been over the past 800,000 years. Good. Now, what else do you guys see, if anything? Does anybody notice anything else or see something weird or something confuses them? Well, the other thing that I like to point out is actually how variable it is. Now, this is the Earth's climate is not static, right? It was -5 and then 5 within 10 to 15,000 years in the Antarctic. CO2 changed as well, but look how dynamic this temperature record is. Look how dynamic the CO2 is. So change of the climate is natural. I'm just going to put that there. We'll talk about what that means in a moment. But climate change is natural. It really is. So I don't want you to get the idea that that the climate is static or anything like that. The climate is dynamic. But as we'll see with humans, it's this part here, how fast it's changing, that is really, really worrisome. So cool. Hope you guys, if you have never seen that, I hope you thought that was cool. I think it's a pretty fun little thing to take a peek at. So our 800,000 years, we learned a bunch of different things. So the first is that CO2 levels did vary between 180 and 300 parts per million over the last 800,000 years. But you'll notice that it's capped at 300 parts per million. It never escaped that. For those of you that pay attention, or maybe you see stuff on the news, global CO2 concentrations right now are at about 420 parts per million. So we are 120 parts per million higher than it has ever been within the past 1 million years. The other thing is some other greenhouse gases, methane, as well as our friend nitrous oxide, are also higher. It's not just CO2 that's higher today than it has ever been. Nitrous oxide and carbon dioxide are also, methane are also much higher. And so this is where we're at. We're warmer than we have ever been. There's more greenhouse gases than there have ever been. And if you want to visualize it, I definitely recommend taking a peek at this. It's a really fun visualization of this record. So take a few minutes to watch this YouTube video. But let's get into this variability, right? I mentioned this variability, right? This changing of Earth's temperature. What the heck is going on here? Why is it so variable? Right? So let's talk about natural climate variability. Now, there's a couple of ones that we're going to discuss, but I'm going to preface this by saying all of these right now simply are not affecting Earth's climate. When we analyze these cycles, these changes, we simply know that they're not affecting what we're seeing today. So we're going to talk about what they are because it's important to know that there is natural variability in Earth's climate. But in terms of the debate about how the climate is changing, we're just simply not going to worry about how they're affecting modern climate change. But again, it is an important thing to know how the Earth's climate changes naturally. So there's modest changes where we see changes in the sun's intensity every 11 years. And I'll show you a graph of that in just a moment. But we have three major cycles that the planet goes through. These are what we canonically call Milankovitch cycles. So we have a shift in the Earth's orbit. So right now the Earth, as many of you probably know, is in an elliptical orbit. It looks like an egg, right? So it orbits at an elliptical, it gets very, very far away and then relatively close. And it does this nice little elliptical orbit year after year after year, right? This path is 1 year long. But every 100,000 years, it shrinks in its orbit. The egg simply collapses into a ball, and you get this very, very short circular orbit around the sun. I'm not enough of an astronomer to tell you why that works. I'm not enough to tell you how any of these work with any accuracy. So if you want to know how Milankovitch cycles work, there's a lot of physics and astronomy behind it that that is beyond my capabilities as a biologist to tell you. But again, that's that shift from this to this, egg to circle, 100,000 years. And then we have what we call the obliquity, which is we change the Earth's angle towards the sun. You guys probably know the Earth isn't perfectly vertical, right? It's not sitting at a perfectly vertical, right, in the air. It's not like a tennis ball sitting on a table. The Earth has a slight tilt to it. And in fact, our tilt in modern times is actually right smack dab in the middle. We're actually at about 23.5 degrees tilt towards the sun. But that tilt varies between 24.5 and 22.5, and it changes about every 40,000 years. Again, this is our obliquity, not really affecting what we're seeing nowadays. And then the final thing we see is what we see in change in the precession, or the wobble of the Earth. But the Earth is so massive, we don't feel it moving, we don't feel it wobble, but the Earth actually wobbles. And its magnetic north changes pretty dramatically on a 26,000 year period. So if we went back in time 26,000 years or so, the North Star would actually not be the actual north that it is today. The north about 26,000 years ago or so would actually be the star system called Vega. And so this changed the precession, the wobble of the planet, also affects how much, what the Earth's climate actually looks like. But all of these, I hope you can see, change the variation and how much solar energy that our Earth receives. An orbit like this means there's more solar radiation make it to the Earth because the Earth is closer, right? You guys probably know if you go close to like an oven, you know that the closer you get to the oven, the hotter it is. That's that. Then we can think about the angle of the Earth. That changes how much solar radiation is directly received by certain parts of the Earth, as does the change in the precession. So all of these affect how much solar radiation affects our planet. And they do warm our planet. They do change our temperature of our planet on cycles. But right now, as I mentioned, these cycles simply are just out of step. They're not impacting what we're seeing in the slightest bit. Now, we also see some pretty other interesting changes in the Earth's climate. Actually, it's some pretty interesting weather phenomenon. You guys probably have heard of these before. We have El Nino and La Nina, so the boy and the girl. They're just Spanish. And they were given to them by Spanish scientists. Actually, not Spanish scientists. They were given to them by American scientists, but affects primarily Spanish-speaking areas of Central and South America. So let's look at what this looks like, because there's text that says what happens, but let's talk about what it looks like. Now, La Nina is the normal part, the normal way things work, where we have these westerly winds that come off Central and South America, pushing all this warm water on all this warm air off this area of the world, warming Australia and the Indo-Pacific Islands, which they're okay with, it's good for them. But what this actually does is it actually, because we're pushing all this warm water towards the Pacific, the western part of the Pacific, I should say, it actually causes cold water to come up into this area. This is what we call upwelling. So it causes cold water to come up, cooling this area of the world. Now you can imagine that given how big this is, that cooling would be substantial, and you'd be absolutely right. This area of the world, when La Nina is in effect, is about 5 to 10 degrees cooler than when El Nino is in effect. So that's how things are normally. Now we have El Nino, where those winds actually shut down and all this warm water starts to pool off the coast of Central and South America, leading to an overall warmer climate in this area. Now remember, the Pacific Ocean is colossal. Every body of land on the planet could fit inside the Pacific Ocean. So changes to the Pacific Ocean in terms of temperature of the water have dramatic effects on climate. So it's pretty big thing. But again, it's a natural thing. It lasts about 9 to 12 months, sometimes longer. But they come basically every couple decades. It affects global climate. The last one was in the early 2000s, if I'm not mistaken. So that's our El Nino and La Nina. Now we have volcanism, or just volcanic eruptions. Now when volcanoes erupt, as you can see from this picture, they produce ash, they produce some acid, but they produce some gases, including CO2, hydrofluoric gases. But the important one here is actually sulfur dioxide, SO2. Now there's a bunch of stuff here, but we're not going to worry about. We're actually really interested in sulfur dioxide. Sulfur dioxide is a pretty cool gas. It's actually a reverse greenhouse gas. That's not a technical term or anything, but that's what I like to call it. Because while greenhouse gases warm the planet, what sulfur dioxide does is it actually cools the planet. It basically acts as like a mirror. It basically reflects solar energy right back out into space. So when volcanoes erupt, yes, they produce a lot of greenhouse gases, but they produce this guy's sulfur dioxide, which cools the planet. And we could see that in a second, but I actually want to just make mention, there's a lot of scientists that say we should actually pump sulfur dioxide into the atmosphere to counter effects climate change. But that's probably not a good idea, just as a note. But let's look at the Earth's average temperature here on the y-axis, and we have time from 1750 to 2000. And you can notice that we have a bunch of volcanic eruptions. Laki, Krakatoa, El Chichon. And you can see every time there's a large volcanic eruption, the Earth's temperature drops precipitously. When Laki erupted, the Earth's temperature dropped by over a degree for several years, but eventually bounced back. Now, what's happening here? Well, as the volcano erupts, lots of sulfur dioxide makes into the atmosphere. It cools the planet, but it only cools the planet for a little bit. So volcanoes can affect our climate in short-term periods. Pretty cool thing volcanoes do. And then the final aspect here is actually variable solar output. The sun goes through what we call sunspot cycles, where the more sunspots we see on the sun, just little black things that appear in the sun, simply means the sun is producing more heat, more energy, thus it could potentially warm the planet. And we can actually, oops, I don't know why I keep doing that. So we can look at that graph here. We see temperature here. This is what we looked at earlier. It's going up and up and up. And you can see our sunspot number. It has this nice cycle every 11 years, up and down and up and down and up and down. And you can see even when we have really intense sunspot cycles, the Earth's temperature doesn't jump dramatically. And the reality is this sunspot cycle is simply out of step. In the past, yes, it has influenced Earth's climate, but what we're seeing now with this global increase in temperature simply is out of step with our sunspot cycle. So those are all of the ways that the Earth warms naturally, the way the climate changes. We have Milankovitch cycles, we have volcanoes, we have changes in CO2, we have sunspot cycles. They all affect the Earth's climate in some way, shape, or form. But this graph really tells you that those are out of step. They're simply not affecting the climate change that we're seeing now. Now, this brings us to this graph. What is causing this? And simply, it's just us. It's really it. This brings the Anthropocene directly back into focus. What is causing this change in temperature? What is causing this increase in CO2? As we see here in the Mauna Loa observations over in Hawaii, global CO2 is rising year after year after year. And as we saw from our 800,000 year record of CO2, as is temperature doing. So humans are causing this. As of August 4th, of this year, it's at 415 parts per million. There's a fantastic visualization here from Vox. I recommend you take a peek at. It's really, really cool. It's about 7 minutes long, so definitely take a peek at it when you have a moment. But it's humans that are driving this change. So I'm actually going to have us take a quick break right here. So let me just pause this recording while we hop back into it. So. All right, just as a forewarning, I'm gonna have to take another break to deal with the electrician again. Not like deal isn't a bad thing, I'm gonna have to take another quick break in a little bit. So just to give you guys a heads up. You'll get another break. But let's dive back in. So let's talk about humans factor into this. Now, remember our greenhouse gases, there's a wide variety of them, but how do humans produce them? And it's pretty straightforward, right? We know this is what the primary composition of greenhouse gases are: water vapor, CO2. Remember, CO2 is the most important of all the gases. But then we start to look at how greenhouse gases are produced by humans, and it's a pretty clear picture as to what the leader is, right? It's still carbon dioxide. That's the most common thing that humans produce. Methane and nitrous oxide are also very, very common. And our fluorinated gases, which we don't produce as much of anymore, but they have a very, very long residence time in the atmosphere, also contribute to our greenhouse effect that humans are responsible for. So this is where we are. Now, where do we get these? Well, the short answer is fossil fuels, right? What are fossil fuels? You guys all know the answer to this, but it's just fuels that we dig out of the ground, right? Coal, natural gas, oil, right? Things that we take, we put into an engine of some sort, we burn it, set it on fire, right? It produces energy for us, powers our cars, powers our homes, powers our factories, powers our entire lives pretty much, right? So our fossil fuels and our consumption of fossil fuels directly ties to our production of these greenhouse gases. And the reality is the rise of these greenhouse gases tracks pretty well with human population. So we looked at this J curve here. Here in blue, we have the world population from about 1,000 years ago, all the way up to modern times. This is in billions of people. And remember, we have this pretty stark J curve that we saw. CO2 tracks pretty similarly, right? It's relatively consistent at about 280 parts per million before the Industrial Revolution. The Industrial Revolution hits about here. Human population takes off, as does CO2, as does nitrous oxide, and as does methane. We're going to ignore sulfate here. Don't worry about it. We're not really going to talk about sulfate at all. So don't you worry yourself about this red line up here. But again, they all track with our population growth, our rapid population growth due to the Industrial Revolution. Now, what powered the Industrial Revolution? The combustion of fossil fuels. So let's look at this over time. We're going to look at a few graphs. For those of you that have never read Vox, VOX, as a news outlet. Vox, it's a pretty good news outlet. I would say it's one of the more credible news outlets out there. They produce beautiful graphs. So I stole these graphs from Vox because they're beautiful and they illustrate the point that I'm trying to highlight here. So let's look at annual carbon emissions by region from 1820 all the way up to 2018. You'll notice that early on it's led by the United States and Europe, but we've easily been eclipsed by China and other Asian countries. And we're starting to see a burgeoning Africa and as well as a footprint from other islands. So that's how things have changed over time. But again, we have that exponential rise, that J curve. Now we can look at per capita CO2 emissions. And you'll notice that early on, US and Europe were the same. But shortly before the turn of the century, the US took off. And the United States, despite having only 300 million people in it, produces more CO2 per capita, i.e. per person, than any other country on the planet, and it is essentially 3 times higher almost than China and Europe, so two of the other large global emitters. Then we can look at sort of the breakdown of all the CO2 that's ever been produced. Where we have North America has produced about 457 billion tons, Europe had about 353 billion tons, and Asia had about 457 billion tons. And we have some other contributions from Africa, Brazil, in Central and South America and the Oceanic Islands. But again, lots and lots of CO2 produced by the 3 leaders here: the USA, the EU, and China, India, and all those other Asian countries. So lots and lots of CO2, billions of tons. We're talking trillions of tons of CO2 are in the atmosphere right now, simply due to human activities. So where do these gases come from? I told you they are from the combustion of fossil fuels, and that's absolutely correct, but it's a little more nuanced than that. So let's look at the production of greenhouse gases by sector, where we have electricity and heat is about 30% of all of our greenhouse gas emissions globally. Transportation, cars, buses, things like that, 16%. Manufacturing, about 12%. Agriculture, 11%. And then there's some other things, land use change and other processes that comprise the remaining 30% or so. But the big groups that we're really going to focus on is this agriculture, manufacturing, transportation, heat, and electricity. Again, comprising about 2/3 of all of our greenhouse gas emissions globally. So let's talk about the bad boy in the room. It's CO2. CO2, as we discussed, it has a natural source. You breathe CO2 out every day. As my sandwich decomposes, it releases CO2. It's natural. But CO2 is balanced by photosynthesis. So for all the CO2 I produce, it's balanced by some plant somewhere on the planet. So natural CO2 emissions are balanced. But man-made CO2 is simply not balanced, which is why it's accumulating in the atmosphere. They come from our fossil fuels. They're non-renewable. What does renewable mean? Well, renewable means that it can be regenerated in a human lifetime. Fossil fuels such as coal and oil take millions of years to form. So they are simply not renewable on a human time frame. But something like wind, something like solar energy, they are renewable because they regenerate fast, again, on a human time scale. But we get these things from a couple sources. So coal used to be the only source of greenhouse gases, but starting around the 1920s, oil picked up, as did gas. But oil and coal still, coal still makes up a huge part of our greenhouse gas budget globally, as well as oil. Gas is coming up pretty heavily. Natural gas is really taking over here in the United States. And cement production, which is a pretty cool thing. So I actually I actually poured a cement patio this summer. So I'm a big fan of cement, not for its greenhouse effects, but I'm just a big fan of cement in general. I think it's heavy, but it's a fun tool it's a fun little material to build with. But cement is actually is actually a pretty cool thing. Now, cement is actually different from asphalt. So asphalt is what's on the road you drive, but cement is like the concretes or the foundation of buildings and things like that. But the way cement is produced is actually through a chemical reaction. So cement has to be dry because these little clinkers, which you sort of see here, they have to have water added to them, and then they react. They have this really cool chemical reaction, producing the hardening that you see. Now, I see clinker, these little things. I don't know if anyone here else is a Star Wars fan, but I hear clinker, and I can't not think of clankers from Star Wars, the Clone Wars and that stuff. So it's not this, it's clinkers, not clankers. And I'm sorry for that nerdy thing, but I can't make the slide and talk about the slide without thinking about these damn little robots. And again, that's just me as a nerdy Star Wars fan. But clinker production accounts for most of the CO2. And the reality is, once clinkers are produced, once they undergo that chemical reaction, they actually release CO2 over time for about 28 days. And so if you think about something like the Hoover Dam, which used colossal amounts of concrete and is actually still hardening to this day, this Hoover Dam as a cement-based thing is actually still hardening, which is it's still hardening, still producing CO2 over time, which is kind of a crazy thing. But cement, as a really important building material, does play not a huge role, as you can see, but a role in our greenhouse gas emissions. Now, CO2 is also hot. For those of you that like The Office, that's for you. But CO2 is hot. Now, wildfires, both natural and man-made, are large sources of greenhouse gases. So when Australia was on fire, when California and the Pacific Northwest are, well, basically always on fire, but when they get really, really bad, they produce lots of CO2. As you burn wood, you release CO2 in the process. So for instance, to put this in perspective, the 2020 California wildfires burned through about 3.4 million acres of land. And the fires alone generated more than 91 million metric tons of CO2, which is about 25% more than California's total emissions from fossil fuels. Now, you guys know California is a monstrous state. It has about 15% of the entire population of the United States. It has a big greenhouse gas budget, but these fires that churn through millions of acres of land produce more greenhouse gases than California as a state on an annual basis. So whenever there's a fire, they produce lots and lots of greenhouse gases. It's really sort of kind of an amazing thing. So our fires, our natural ones and our man-made ones, produce a lot of CO2. Most large wildfires, as a note, are man-made by someone like doing like something stupid, like not putting out their fire in a campground, stuff like that. There's very few natural fires that happen. Most of them are man-made. I think it's like 95% of all fires are man-made at this point. So just to let you guys know that. Now this brings us to methane. It's a pretty cool group of pretty cool gas. Now it's naturally produced by by a group of microorganisms called archaea, and it's actually consumed by a group of bacteria as well. So there is a natural source of these things, but the major source of methane as a gas is actually our cows. So this comic is actually wrong. This cow is asking the farmer to pull his hoof, because people like to think methane comes from cow farts, but methane actually comes from cow burps. Why is that the case? Well, you guys probably know that cows have a multi-chambered ruminant stomach. Inside their stomach, they have these microbes that when they break down the grass and the other stuff the cows are eating, they produce a little bit of methane, which the cow then burps out, just as a note. So cows are a big source. Cows alone, if I'm not mistaken, and I could be wrong about this, but cows alone account for about 8 or 9% of the total global warming that we're seeing today. So cows are no joke in terms of greenhouse effect. Now, natural gas, which is simply just methane, as well as pipeline leaks, add to the amount of methane in the atmosphere. Wet rice paddies, so wherever there's rice grown, methane is produced. Coal mines are really, really common. As we dig up coal, we release methane out into the world. And then landfills are also a pretty large source of methane. As the food in our landfills breaks down, the microorganisms produce methane. So methane has lots of sources, but the one I actually want to talk about that will become important in a few classes when we talk about waste is actually food waste and its contribution to our greenhouse gas footprint. Give me one second, guys. I'm sorry, I gotta talk to the electrician. 1 second. All right, so let's get back into it. So where we left off, we were talking about food waste. And so we have total greenhouse gas emissions of without any land use or change or anything, just by the decomposition. And we have China and the US are number 1 and 2, as we are with a lot of things. And then we look at food waste. It's number 3. So if we added up all the food wasted around the entire planet every year, the reality is all that food waste would produce enough greenhouse gases to be considered the 3rd largest country in terms of greenhouse gas production, just food waste, which is kind of an amazing thing when you think about it, right? Just food waste. More than India, which has a population of now, what, 1.4 or 1.3 billion in that ballpark. So it's huge amounts of greenhouse gas produced just by food waste. Now you might ask yourself, where is the food waste generated the most commonly? Is it businesses? Well, households account for about 42%. Consumer facing, i.e. like realtors, like, Chipotle, Wendy's, stuff like that, are about 40%. Very little food, about 16% of the food waste is from farms, and about 2% is from food manufacturing. Those food manufacturing companies, they don't waste a lot, which is, I guess, probably a good thing. So lots of greenhouse gases produced from our food. So when you get ready to throw some food away, think about your greenhouse gas footprint. Now, this brings us back to our friend nitrous oxide. Nitrous oxide, as we discussed, naturally occurs because of microscopic organisms as well as lightning. Go away. But it is commonly produced via the combustion of fossil fuel. And so as we combust fossil fuels, sometimes we take some of that nitrogen in the atmosphere and we make nitrous oxide from it. And that's about 10 to 12% of all nitrous oxide produced by humans. But a lot of our nitrous oxide actually comes from the agricultural sector. So non-organic farming, as well as organic farming, but certainly led by non-organic farming, produces about 78% of all human produced nitrous oxide. Then we see other things, like combustion, chemicals, things like that. But most of our nitrous oxide that we produce, and remember, nitrous oxide is a very potent greenhouse gas, comes from agricultural soil management. In particular, it comes from agricultural soils that we dump a lot of fertilizer on. The microscopic organisms that live in these agricultural fields, when they're exposed to lots of fertilizer, they produce a lot of this greenhouse gas. So they play our agriculture, where we get our food from, plays a large role in nitrous oxide. Now we can look at this between sectors. You can see cotton and almonds actually produce the most per sort of hectare of any crop out there in terms of nitrous oxide. We also see wheat and tomatoes, lettuce, walnuts, and so on and so forth. So not all foods equally produce nitrous oxide. Some produce way more, like cotton and almonds. So it's not an equal production. Now, the final thing I'll say about our friend nitrous oxide is actually what it does to the ozone layer. Now, nitrous oxide, when it is produced, it actually reacts with ozone. And so nitrous oxide, when it's in the atmosphere, it can react with ozone and actually do one of two things. It can produce nitric acid, which is HNO3, which actually contributes to acid rain. But when it does react with ozone, it depletes the ozone layer. So while we banned gases that do deplete the ozone layer, we are still producing one very, very potent greenhouse gas that also has a very strong effect on the ozone layer. So nitrous oxide is a double-edged spear right here. Affects the ozone layer, affects our climate as well. So that's why I liked nitrous oxide. As I mentioned, I really liked nitrous oxide when I was in grad school. By far my favorite greenhouse gas. So those are greenhouse gases. Those are the sources from humans. Now, if we know this trend exists, what does this mean? What does the rising global temperature mean? What does the rising CO2 concentrations mean? Well, when we look at across the planet, globally, we are about 1 degree centigrade warmer than pre-industrial times, so before the 1850s. CO2 right now is greater than it's about 420 parts per million, and to put that in contrast, before the Industrial Revolution was less than 280 parts per million. So we have more CO2, almost double just for the sake of pointing that out. And we have a much warmer planet. Now we can sort of see this, where you can see the temperature change in decade, and you'll notice that cooler colors are cooling areas of the planet, and there's not very many of those. There's some in the southern Antarctic seas here, and there's some here in the Pacific Ocean. But most of the planet is red here. It's on fire. So most of the planet is warming. But it is important to note two things about this figure. The first is that it's not every place is responding the same, right? Some places are cooling, some places are warming, but by and large, the planet is warming as a whole. And the second thing is certain parts warm significantly faster than others. Look at us here on the East Coast of the United States. We're getting hot, hot, hots. Look at Europe. Look at the Arctic. Climate change is not uniform over the planet, but globally we are seeing trends of warmer temperatures, but some places are simply going faster than others. So it's like when you watch a race, right? Some runners just run faster than others, and that's what we're seeing here. New England, we're winning that race with the Arctic. You could look at lots of the Atlantic; they're losing the race because they're simply not running as fast as we are. So we have a pretty we're kind of at a planet on fire. That's kind of where we're at, right? We're much warmer than we were. Now, we can actually talk about a really important group of scientists, which is the IPCC. Now, the IPCC represents, or the Intergovernmental Panel on Climate Change. They are the single most important scientific group surrounding climate change. It's not just scientists that work on climate change, but it's also economists, there we go, doctors, there's nurse, there's any type of person you can think of. The IPCC has those people in it. But more importantly, when we're talking about this, which is a basic science idea, there's 2,500 scientists that are represented in this organization, and they span 130 countries. And so this is a really important group of people. They're basically the world authorities on climate change. You can read about them here at their website, but they are a very, very important group of scientists, a huge group of scientists, and a very, very diverse group of scientists. And so when they tell us something about climate, it's got a lot of backing behind it. It has a high degree of certainty behind it. And so when we were talking about plastics the other day, and I gave you sort of the scale of, scientific certainty, like smoking causes cancer, and zero certainty as in like the earth is flat, the certainty about climate change as a feature of our planet and humans' role in it is basically at the level of certainty of smoking causes cancer. We are very, very sure about this. And there is basically international agreement about the seriousness of this problem that we face. And the IPCC has been leading the way on this from this. So let's look at IPCC, because one of the things they do is make projections. So let's look at some of their projections where they have emissions from fossil fuels and cement. And then we have time from the 80s out into the 2100s. And you see that we basically see our 2016 is here in that ballpark. And you see all these varying estimates. So CO2 either is projected to get really, really high, get slightly higher, get higher for a bit, and then come down, or go down over time, depending on what actions we take essentially as a society in response to this problem. Now, what does that mean for temperature? Well, it should be pretty straightforward to think what that means for temperature. If we go really, really high in CO2, our planet is projected to warm much, much higher. If we go slightly higher, it's still expected to get quite warm. If we reduce emissions, we're expected to decrease our global to decrease the effects of climate change on our planet. And that's sort of one way to look at it. We can look at it here, global surface temperature change from 42 different scientific models. And depending on what action we take against climate change, we either get really, really hot, sometimes 12 degrees hotter, or we don't get too much hotter and we sort of reduce our emissions and keep things sort of at a livable level for the planet. So really important group of scientists, lots of projections, but if things keep going the way they are, we anticipate to follow this red line. We anticipate to follow this red line to get warmer and warmer and warmer if we continue at what we would like to call business as usual, simply not making any meaningful changes. So that's climate change. That's the underlying science. That's our atmosphere. That's how warming works. That's the sort of most important models thinking about how CO2 is projected to change over time. So what's happening because of this? What do we anticipate? What are we seeing now as this comic depicts? Or what do we expect to see going forward? Because this comic really tells you it's not just a far off problem. It's a now problem. We're seeing global heat waves like we've never seen before, whether it's here in the United States, whether it's in the Middle East, whether it's in Europe. We're seeing fires like we've never seen before. So this is a now problem, but what are some of the future problems we depict? So we're going to talk about these problems. Some of these are things that we've touched on a little bit, but ones that will become a little bit more clear as we talk about. Now, as we put more and more CO2 into the atmosphere, our ocean actually starts to take a role in absorbing CO2. Of all the CO2 produced, our oceans absorbed about half of all CO2 produced. Why does that happen? The oceans are just massive and gases dissolve into the ocean. So because of how massive the ocean is, it absorbs a lot of CO2. But as ocean starts to absorb more and more CO2, we actually have this really funky chemical reaction that happens. As CO2 dissolves into the ocean, it reacts with water, and it actually forms a very, very weak acid called carbonic acid. So for those of you that have ever drinking, say, a soda or a seltzer or even beer, you know that they're a little bit acidic, right? They have a tang to them. Why is that? Well, it's because sodas and beers and seltzers, they have CO2 dissolved in them. And that CO2 reacts with water, making soda and seltzer slightly acidic. Now, that's not a big deal for you, though your teeth don't like it. Your enamel hates acidic sodas, just as a note. But marine life really hates it when the pH starts to change. So what happens is we produce a little bit of acid. It reacts with carbonate. Now, carbonate is a really important molecule. Carbonate is actually one of the primary components of the exoskeletons of arthropods, so crabs, lobsters, things like that, as well as mollusks such as oysters, crayfish, mussels, any sort of shelled organisms. You think when there's more CO2 in the water, they have a much harder time forming a shell. And it's just not a good picture for our shell forming friends in the ocean. And you can imagine if the more and more CO2 produced, the more acidic the ocean gets. And as the ocean gets more acidic, it means it's a harder time for marine life. Their shells go from happy to sad, and eventually they simply can't form a shell. And you can imagine that this is just a direct effect on marine life. But if you think about the economic effects of this, the shellfishing industry to a state like Maine is billions of dollars a year. And if this happens to, if this keeps happening, the places like Maine that so heavily rely upon shellfishing for their economy will also be strongly affected. Now, we also know that there's direct effects of more CO2 in the water on our coral reefs. So coral reefs, when they're exposed to high levels of CO2, as well as high temperatures in the water, because of changes in the global temperature, they go from nice and happy to basically being dead. So when corals get stressed, they die, as most organisms do, of course. Stress is a huge killer. It's not just a human killer, it's an everything killer. And CO2 and warmer temperatures stress the heck out of corals, and it causes corals to die. And it's not just our corals, it's not just like crabs, but remember, it's also commercially viable things. We can see oysters At a pH of 7.5, their shells just simply aren't as thick, as strong as they would be at a normal oceanic pH. So oysters, crabs, anything that forms a shell with more CO2 is in for a hell of a ride because it's not going to be safe in the ocean or even say fresh water for these organisms. Now, one thing we touched on a little bit in our air class is actually air pollution. So the more CO2 we go in the atmosphere, the more CO2 we produce as a direct result of our activities as a species. So more CO2 means more combustion of fossil fuels, but fossil fuels are dirty, right? So as we produce more and more CO2, we produce more pollution, more air pollution. And there are numerous effects of air pollution on human biology. So let's look at this handy dandy pyramid of effects from air pollution, where as you go up the pyramid, death obviously being the most serious thing, but the effects, the severity of the effects becomes more severe. And as you go down the pyramid, the more people it affects. So the wider the base, the more people it affects. So air pollution, even in say not large city, has pretty strong effects on lung function, inflammation, as well as your heart. People that live in city oftentimes live slightly shorter lives than people who live in the countryside. Then as we go up the chain, we start to see respiratory things, asthma, over medication use. Then we get higher, lots and lots of doctor visits, lots of school absences, lost work days, so economic effects. And then we see ER visits, hospital admissions, heart attacks, and still more economic effects. And eventually, obviously, probably the worst thing that could probably happen is that air pollution kills you, right? And so I actually want to focus on actually, give me one sec before I talk about that. I want to focus on this this economic parts right here in just a second, but I want to just sort of show you how deadly air pollution is. So particulate air pollution cuts off on average about 1.8 years of human life on average. And that's more than smoking. That's more than alcohol and drug abuse, more than unsafe sanitation. So particulate air pollution is arguably one of the greatest threats to human health globally. It really is. Particulate air pollution is a nasty killer. And again, there's lots and lots of things that go into this: pneumonia, strokes, heart disease, lung things. Any number of health effects can be linked to this. Now, this little infographic from the World Health Organization, I couldn't find an updated one, but this infographic basically tells you about 7 million people die prematurely due to air pollution. That figure has actually been recently revised to actually be closer to 10 million people annually, just as a note. And that might not seem like a lot of people, but 10 million people is still a lot of people that die prematurely, even relative to the large population size on this planet. And if CO2 gets more and more, if we produce more and more CO2 over time, this number is just going to get larger and larger and larger. Now, I'd like to come back to the economic effects of pollution. And so this is actually this is some data from our friends at the Department of Commerce. And this is loss of working days due to air pollution. So lost working days, and this is all in millions here in the United States. So we lose a crap ton of work days every year, millions and millions every year. Restricted activity days and minor restricted activities, again, millions and millions on a yearly basis. And then we sort of look at projections of CO2 going forward. What does that look like going forward? Well, it's expected to essentially triple, right? So more CO2, more lost working days. And you can imagine this has a pretty large economic effect on not just our economy, but the global economy, right? You're talking about large percentages of GDP per year are lost strictly due to air pollution, which I think is a truly remarkable thing when you think about it, right? Just how much cash is lost every year because of particulate air pollution. So more CO2 is bad for air pollution, but it makes our ecosystems warmer. Now, as I mentioned, when corals get stressed by heat or by more acid in the water, they get bummed out. And we do know coral reefs globally have declined by almost 50% and are actually expected to completely disappear if we don't do anything to stop climate change by the year 2035, 2040, in that ballpark. So our warmer ecosystems spell trouble for our coral reefs. And you might look at coral reefs and say, oh, that's a bummer. They're just really beautiful. But the reality is coral reefs as a ecosystem are really important for humans. They're not just for tourism, but they actually provide about provide protein and almost the entire sole protein source for about 2 billion or so people on this planet. So if coral reefs go away, so do the vibrant fish communities that help feed huge numbers of people. So it's not just like Australia loses money because people can't go to the coral reefs for tourism. We're talking about lots and lots of people losing their livelihoods, lots of people losing their most important source of protein. So the loss of corals has a multitude of effects on our planet. Now, this brings us to one other aspect of as our air gets warmer, our oceans also get warmer as well. I've already made mention of that. But the thing about water is when water warms, it actually expands. You could do this experiment if you wanted to. You could actually measure out, if you had like a measuring cup, you could measure out, say, a cup of water, boil that cup of water, and then try to pour that water back into the same measuring cup. It simply won't fit. Why is that? Well, as water warms, it expands, right? And so as the ocean gets warmer and warmer water, the volume of the ocean actually rises. And as the ocean expands and gets higher and higher and higher, it allows tides, it allows floodwaters from the ocean to make it into places it actually never could before. So this is actually some data from our state government here in Massachusetts, where we have days of coastal flooding in about 10-year periods from the 50s all the way up to modern times-ish. And then we have orange here. It's driven by climate-linked sea level rise, so increases in the ocean's levels, and blue, which is what have occurred naturally. And you'll notice that back in the 50s, they were about in balance, and they were in balance all the way up until the mid-90s when human climate-linked sea level rise was really driving increased days of coastal flooding to the state of Massachusetts. So much so, it's about 1/7 of the year nowadays that we have some level of coastal flooding in the state of Massachusetts, which I think is pretty remarkable. And so I'd like to just show you what this looks like, because it's really not something we think about all that often. But when I was at UMass Boston as a student, also as a teacher, but mostly as a student, I would actually see scenarios like this quite often. So for those of you that know where this is Morrissey Boulevard. This is Dorchester Bay over here. The gas tank, that's got the stripes on it, is about over here. And UMass Boston is somewhere back here, like half a mile or so back here. And this is the bridge that goes over the ocean and stuff like that. And so this is just a really common picture from my picture library where it would be snowing, or we'd have a storm of some sort, and the coastal flooding would get so bad, it would completely flood over Morrissey Boulevard. And again, events like this, they are natural, right? They do occur, but the frequency by which they're occurring is simply increasing over time. And you can imagine, like, this is a minute amount of flooding, right? This isn't too bad. This drains back, they clean it up. It doesn't cost the state very much money. But you can imagine if we had much more severe flooding in, say, like the financial district of Boston, maybe that's something that causes much, much more concern to policymakers here in the state. So let's look at how sea levels have changed globally. We have sea level change, and this is relative to the mean. Sorry, it's shoot. Oh my goodness, I'm so sorry. I'm blanking what this is relative to. I'm so sorry about that. I'll think of it in a second. But we have tide gauge measurements here from the 70s all the way up to nowadays. You can see we've increased by about 4 or so centimeters in that time period. So the sea levels are getting higher, and they are projected to get higher and higher and higher over time. So the thing to point out here is that 4 centimeters might not seem like a lot, right? You might say, oh, 4 centimeters, that's less than 2 inches. That doesn't seem like a lot. But when you think about a 2 centimeter increase of the global ocean, that starts to become a significant amount of water. And so to put that in perspective, when we think about tides, right? When we think about tides here in Massachusetts, right? Our tides here in Massachusetts swing by 8 or 9 feet on a daily basis. All of those tides, that 6 to 8 feet change in tide levels here in Massachusetts, is actually only caused by a 1.25 centimeter change in water level due to the moon. So little amounts of water at the global scale really start to add up. So small levels might not seem like a lot, but when you're talking about as voluminous amount of water as the oceans, 4 centimeters is no joke. So let's look at some sea level maps here. So we have change in sea level. I hate the way this map is colored, but it's a really good map because it's colored the exact opposite of the way I would like it to be colored, just as a note. But we have changes in sea level in centimeters. So bluer colors means an increase in sea level. Redder colors means a decrease in sea level. And you notice there are some areas of the planet where there is pretty substantial decreases, right? Down here in the Arctic and a few other spots, right? But most places are blue or experience no change. But you can look here on the eastern seaboard where we see some pretty stark blue here. And in fact, the eastern seaboard of the United States is actually experiencing some of the highest rates of sea level change that we actually see on the planet. But the planet as a whole, the oceans are simply getting more voluminous. Now, there are two factors that contribute to that. So one is just the oceans getting warmer. And remember, as the water warms, it expands. We call this thermal expansion. However, there's another aspect to global sea level rise, which is actually meltwater from our landlocked glaciers. So places like Greenland, but not places like the Antarctic, but places like Greenland. So we can look at global sea level here, and we can see that when we start to factor in both of those, thermal expansion and meltwater, meltwater contributes quite a bit more than thermal expansion of water to our rising sea levels that we're observing. So melting of glaciers is a big deal. And so we can look at just examples of this. We have the Peterson Glacier in Alaska, if I'm not mistaken, where a picture taken in 1917, this really, really awesome looking glacier. It's on land, so it's not like sitting in the water already. You guys probably know that, when something is floating in the water, it doesn't, when it melts, like ice when it's sitting in water, when it melts, doesn't increase the volume of water at all. It has to be on land and then dropped into water, right? So we can look at the Peterson Glacier here, pretty cool looking glacier. Fast forward to 2005, so basically less than 100 years later, and we see the Peterson Glacier is basically completely gone. It's replaced by a nice little grassland here. The glacier exists a little bit up in these mountains, right? You can see the mountain here and here and in the background. But again, the glacier that still is there is very, very small. We've lost huge amounts of glacier regions across the globe. Which is pretty stark when you sort of see these side-by-side comparisons. Right? Now, it's important to note that it's melting of landlocked ice, and the biggest sources of landlocked ice are Greenland as well as the Arctic Circle. So ice that exists on our ice that exists on our land. So the melting of Greenland, and I'm sure you guys probably hear about melting of Greenland all the time. It's a serious deal because the more Greenland melts, the more our landlocked ice melts, the higher and higher our oceans go. So what does this mean for low-lying places? So we'll pick on Florida because Florida is a funny state. But as we discussed with the Everglades, so the Everglades run from here all the way down to Miami. Florida is a very wet state. It's a very, very low-lying state. And so areas like Florida, or potentially places like Bangladesh or Thailand, places that are very, very low, are actually expected to see some pretty severe effects of sea level rise. So we could look at the map of Florida in 2001. And then we could look at projections of Florida into 2100. So lots and lots of sea level rise. And you can see Florida is basically mostly submerged at this point, right? You see huge parts of Florida. The Miami area is basically gone, right? So Florida as a low-lying area and other places around the globe that are low-lying relative to the ocean are expected to see some pretty serious effects of sea level rise. Now we could do a kind of a cool little thought experiment. So I found this one a couple of years ago, but what would happen if we melted all the ice on the planet, right? There was no glaciers, there was no Greenland left. And the effects of massive and catastrophic ice melt on the planet are severe. So you can look at low-lying cities like Houston and New Orleans, Miami, even Boston and New York, completely submerged by global sea level rise. And so sea level rise is no joke. It is projected to affect lots and lots of people globally, billions of people globally, especially people that live in low-lying areas. And a lot of places that are low-lying oftentimes are very, very poor. And that's kind of a nice, kind of a theme we'll discuss later in the class about sort of who's going to be hurt the most because of climate change. But sea level rise is not just like a Florida thing, right? It's actually a Boston thing. So let's look at some data from Boston. So if you guys have never discovered this, there's a the city of Boston has what's called the Climate Ready Boston action plan. It's a pretty cool thing. And in part of this, they have these climate maps. They're fun to play with if you like to sort of look at these things, I guess. But this is the 2070 high tide. So the normal high tide doesn't, go this far. But projections of what sea level will look like in 2070 show us that high tide is expected to intrude into some places where we actually never did before. So we can look at a really sort of populous set of areas here, right? We can look at like East Boston, Chelsea, Winthrop, or even the financial district of Boston, Cambridge and Somerville as well. These places are expected to see some pretty severe high tide flooding, not like storms or anything like that, but high tide flooding. Again, that's due to sea level rise. How many billions of dollars of real estate are tied up in this area of Boston alone? And how much would that affect the Boston real estate market? Now, what about coastal flooding? We could see 2070 coastal flooding projections. You basically notice Boston is basically an entire bit of green, right? But it's not just Boston, right? It's, down into the Winthrop and Revere and Chelsea and all these areas. Lots of areas of Boston are projected to experience coastal flooding. And these are areas that actually never experienced coastal flooding before, right? The financial district, the North End, the Mass General over here, right? Lots of places are expected to see coastal flooding in the future due to sea level rise. And then the final map I'll show you, but I do recommend you play around with them because again, they are fun to sort of see, is actually an overlay. So we have coastal flooding, high tides, and then so blue and green here. And then we have this sort of rainbow of colors, which is economic and social vulnerability. Now, what does that mean? Well, these are areas that are either really, really poor or, not doing so great, or they have people that are elderly, disabled, or they're neighborhoods that have a high proportion of persons of color. And so you'll notice that the overlap is really, really high, right? Lots of high tide, lots of coastal flooding overlaps areas that are already struggling in the Boston metropolitan area. And so one of the key takeaways of this is, yes, sea level rise is a big deal. The people that are actually expected to be hurt the most because of climate change are actually people that are already struggling in some way, shape, or form. So definitely recommend taking a peek at this. It's really cool to look at, to see. You could find your house on it too if you live in this area. It's kind of a cool little thing to take a peek at. So definitely recommend taking a peek at these climate maps. The city of Boston does take climate change very, very seriously, unlike a lot of cities and states around the country. So it's good to sort of see what Boston is thinking about, what they're trying to do to prevent climate change. And you guys go to school in the Boston area, but I know many of you probably also live in the greater Boston area as well. So let's talk about a really cool aspect of climate change that is right up my alley. And this is actually climate change and disease. So for those of you that actually don't know this, the Centers of the CDC, so the Centers of Disease Control, was established in Atlanta. And it wasn't established in Atlanta because there was awesome real estate there or anything like that. The CDC was established in Atlanta because the United States actually used to have a problem with malaria. For those of you that have never heard of that, surprise. So the CDC was established in Atlanta to help fight and combat malaria. And we don't have malaria in the United States right now. So it's kind of a cool thing. But the reality is that malaria is actually starting to push more and more back into the United States. So why is that the case? Well, warmer weather actually does one really fascinating thing. Warmer weather actually means there's more insects, more active insects. And that's a big deal because the deadliest organism on this planet is actually the mosquito. The mosquito alone kills millions of people every year via the diseases that they carry. And mosquitoes are just one type of disease-carrying insect. There's lots and lots of insects out there that carry diseases. But warmer weathers means two things. These insects are more active, which means they're more likely to pick up diseases and then spread them. But it also means there's going to be more insects. And so as the planet gets warmer, these insects are going to go crazy. And we're thinking about two things here. More cases of, say, malaria or West Nile or Lyme disease, but also insects, because of the changes in the climate, are going to protrude into areas they never were before. So the thing I'd like you to sort of think about is like, okay, we used to have malaria in Georgia, but think about as the planet warms and warms, getting malaria in, say, places like France, getting malaria in places like Pennsylvania. So warmer weather means more insects, more transmission of the diseases that insects carry, but also insects to go into new places they never could before. And when we think about a disease like malaria, malaria is one of the single greatest scourges on this planet right now. It infects 80 million people in tropical regions. And those people have been living with malaria for thousands of years. Can you imagine how deadly malaria would be if it came to Pennsylvania, where they've never experienced malaria before? So climate change and disease is a very, very fascinating topic for me. It could be an entire class all by itself. So I'll leave with you this link to the CDC, really cool looking at climate change and the effects of health. And insects are one of the sort of the biggest aspects of that. Now, a really sort of easy thing to understand about climate change is that as we get warmer, the way the water cycle functions is going to change. So more heat, warmer planet leads to more evaporation, which leads to less fresh water, more drier areas of our country. So we talked about lots and lots of water withdrawal in the water class, but we are expected to see heavier and heavier water withdrawal due to warmer climates to feed our crops and for ourselves, but also a depletion in our natural water sources, whether it's the Great Lakes or our rivers, again, due to warmer weather, more evaporation. And we can sort of look at this as in changes of precipitation as well. So more warmer climate leads to more water vapor in the atmosphere, which potentially can lead to more precipitation. Now you might think more precipitation is good, and you're right to an extent, right? Precipitation is obviously really, really important, but actually one of the sort of interesting dichotomies you see is states like say North and South Dakota here, which grow quite a bit of beans, legumes for us and soybeans and stuff like that, actually worry less about too little rain, and their crops most commonly get damaged by too much rain. So too much rain, whether it's in this area of the world or potentially, too much rain in, say, Michigan, which grows a crap ton of our food, or too little rain in places like California and this American Southwest, means not so good things for the way we grow our food, but also for the people that live in this area, right? You can imagine Arizona. They don't have enough water. How are the millions of people that live in Arizona going to get drinking water, right? And the final thing I'll just say about water is the second to last thing I'll say about water is actually scenarios like this, where we're actually seeing an expansion of deserts globally. So this is in Australia. You see this perfectly straight fence. We see the desert here on one side, and then we see this area here on the other side. Happy little miniature little grassland here. And we're actually seeing this part of the world starting to encroach in this part of the world. Deserts are getting larger globally. It's not just here in the United States. It's in China in the Gobi Desert. It's in the Atacama Desert. It's in the Sahara Desert. Deserts are getting larger globally because of more and more water loss globally. And it's kind of a sad thing. Some of you guys might have read about what some African nations are doing. They're actually trying to plant billions of trees along the southern edge of the Sahara Desert to try to basically create a green wall to stop the Sahara Desert from spreading any farther south. So this expansion of desert, it's also called desertification, is a big deal globally, in particular in the places that are already very, very dry. And the final thing I'll say about water security is actually here in Massachusetts. So this is a map from 2016, but this actual map actually existed in early May of this year, where most of the state of Massachusetts has basically been in a perpetual drought for year after year after year. It was only this year that we got out of the drought because we had so much rain in May and June and somewhat in July. But drought is not just something people in Africa face. It's a reality for even here at the local level too. So definitely don't want to forget that. Drought is a big deal everywhere. So this brings us to some other interesting effects on your average everyday life, which is actually changes in nutrition. So one thing we see with changes in nutrition is that as the planet warms, it means plants have more water stress, i.e. they simply don't have enough water, which means if you're a farmer and there's not enough water to grow crops, it means there's likely to be less crops and crop variety as well. So you might not think doesn't sound like a big deal for here in the United States, right? We have so much crops and stuff like that. We don't struggle with nutrition by and large. However, when we think about areas in, say, Africa or potentially poor rural areas, which are about, a significant portion of our population, this is much more severe of a problem. right? If you have to limit what crops you grow because it's simply too hot, it means we're likely seeing changes in the nutrition people are getting. So let's take a look at the maps here. So we have a map of the United States. So changes in agricultural yields. You can read about this here, but it's a projection of 2080 to 2100. And you can see large parts of the United States up here are projected to see increases in agricultural gains, but most of the places where we grow our food, so the breadbasket here, Michigan as a state that produces a huge amount of crops, California, again, a huge amount of crops, and all these Midwestern states, which produce most of our food, obviously the food that we don't import, of course, are expected to see significant changes in agricultural yields. Why? It's simply not going to be enough water, or potentially there's too much water. So not a good thing, not a good thing at all. Now, the final thing about our food, which you guys might find interesting, I always find it interesting. There's been some really cool research lately about the effects of more CO2 on the nutritional value of crops. So when scientists subject crops to 2050 projections of CO2, crops get actually a little bit stressed by that. And so when crops get stressed, they actually start to lose some of the nutritional value. And so crops that were subjected to higher levels of CO2, you can read about this here from Harvard University, they lost about 10% of their zinc, 5% of their iron, and about 8% of their protein content, which in a place like the United States, where overindulgence is the norm, not a big deal. But in places that are very impoverished or already have problems with food security, this is a big change, especially the part of protein. Losing 10% of your protein and you're already struggling for food is a really big deal. Now, one last aspect of food that I think you guys will probably hate is actually what's happening to coffee. So we actually know varieties of coffee, both wild and cultivated, are actually struggling worldwide. And so you can take a peek at this here. Definitely take a peek at it. But about 60% of wild coffee species are actually risked for extinction, and most coffee is declining worldwide, which sounds awful. I don't know about you guys, but that's one of the scarier aspects of climate change to me, is coffee might go away in some time, in some of our lives, which is kind of an awful thing to really think about. And I like these two quotes, so I'm just going to quickly read them. And the author from this study says, we should be concerned about the loss of any species for lots of reasons, but for coffee specifically, I think we should remember that the cup in front of us originally came from a wild source. So if the wild sources are dying, our coffee varieties that we depend on are also likely to start dying. And he sort of finishes by saying, we think at least 60% is conservative, unfortunately. All things are very tightly interconnected. And so as we deforest more wild tropical areas, as climate changes, our beloved coffee is expected to go down the tube with it. And if you don't like coffee, that's cool. But I will also make mention of two other really awesome crops. The first is grapes, in particular the grapes that we use to produce wine. Those are also being stressed by climate change and are projected to see significant changes in their production in the future. And for those of you that like beer, we're expected to see significant declines in the production of hops globally as well due to climate change. So if none of those three things excited you, there's lots of other reasons to be worried about your food. But at least for me, when I see the decline of coffee, I get a little bit sad because I like myself a nice fresh cup of coffee every morning. So lots and lots of food is expected to be in short supply going forward for a variety of reasons. Now, the other thing we're actually seeing is some pretty severe changes in weather. And these are sort of interesting to think about, because one of the things we're actually seeing is actually a shift in production of crops. So we can actually look at the viable range for wheat production here in yellow. And 2050 projections actually tell us that we're going to be able to grow wheat significantly higher in latitude, well into Canada, approaching the Arctic Circle up here. So crops and plants are shifting their growing ranges, but they're also changing what's called their phrenology. They're flowering differently. They're growing for longer. Plants are kind of changing in response to the changing climate, which is a good and a bad thing. Being able to grow, more wheat up here sounds good, but that also means we're likely eventually not going to be able to grow wheat down here. And so kind of a cool thing. Now we're also seeing changes in precipitation. So some places are getting wetter, but droughts are becoming far more frequent and far more widespread, not just here, but also globally. We're also seeing a shift in storms. Now we're seeing less of more storms. So last year was a pretty bad year for storms in terms of hurricanes. We ran out of names, as I'm sure you guys probably saw. We were into Greek letters We had like Hurricane Iota. I think that was that the last one? I think that was the last one. So storms are becoming a little bit more common, but the big problem with the change in weather is actually we're seeing more intense storms. So we're seeing more Category 4, more Category 5 storms as the planet gets warmer, which is not good. All right, think about the ongoing damage that still is happening, that happened in Puerto Rico due to Hurricane Maria. Think about how hard Katrina hit New Orleans. Think about how hard Hurricane Harvey hit Houston, or Hurricane Andrew hit Florida in the 90s. These monster hurricanes, they're no joke. And it's not just a joke to like people, like they kill people, but think about the economic cost of storms. They're huge. And then the final sort of thing is if there's less precipitation, it means to more fires, right? You guys, I don't need to tell you guys about all the fires that are happening out in California, both currently and in the past, or that Australia lost well over 1 billion animals to their gargantuan wildfires that they had a few years ago. So less precipitation leads to drier areas. The fires we saw in California now and in the past, and the monster fire we saw in Australia, while fires are natural in those areas, simply they are climate induced. There's no guesswork around that. They are climate induced. They're not due to poor forest management. They're just due to less precipitation, leading to drier forests, meaning that fires are more likely to get larger. So now, one other thing we're seeing because of warmer weathers is actually range shifts in insects. Now, we talked about pests like mosquitoes expanding, but we're also seeing agricultural pests expanding. So one particular cool pest that I'd like to just quickly make mention of is actually the spruce beetle. They're a pretty cool looking beetle because I don't know, I always think they look like little hedgehogs because they're all the little hairs on them. But these spruce beetles, they lay their larvae on spruce trees. And their larvae bore into trees, as you can see here, and they eventually kill the tree. It's just the way they work. And so we can actually look at the range of the spruce beetle here in red. And then we can look at black, which is the spruce range. That's in 2000. Projections of the spruce beetle range are expected to essentially cover the entire range of the bark of the spruce trees, which for our spruce trees is not a good thing. So pests, both agricultural and natural, are expected to shift their range as well. Now, the final sort of effect about climate change that we're going to talk about is actually the most damning part about climate change, which is climate feedback loops, where we change the climate and then the climate pokes itself to change even more. So let's talk about these two things. The first one we're going to talk about is the melting of ice. So we do know globally, the Arctic Sea, so up north, is about half as thick as it was 30 years ago. And we're seeing massive amounts of ice shelves break up and completely disappear. Now, as we talked about, ice is very, very reflective, right? It has a high albedo. So the Arctic, if it was very, very covered in snow and ice, it would reflect a lot of heat back up into the atmosphere and out into space, cooling the planet. But as the Earth gets warmer and warmer and warmer, it melts more and more sea ice, which changes the albedo of the planet, in particular the Arctic, which leads to a lower albedo, i.e. more heat is absorbed in the Arctic as well as the Antarctic. What that does is increases the amount of absorbed sunlight, which increases the temperature, which then in turn increases more sea ice melting, leading to more ocean exposed, lowering the albedo of the planet even further. And we have this little 6 cycle here where as the planet gets warmer, we have less ice, which leads to lower albedo, which leads to more warming, which leads to more lost ice, and the cycle repeats and repeats and repeats. So climate change feeds back into itself, pretty damning here in the Arctic with ice. So that's one feedback loop, and we understand this one pretty well. But this second feedback loop is actually one that we understand super poorly. And of all the things that we know about climate change, the microscopic organisms that live in the Arctic is actually the one we understand the least. So let's talk about the Arctic. Now, the Arctic has permafrost. You guys have probably heard of permafrost before, but permafrost is simply a short little way of saying permanently frozen dirt. So dirt that is perpetually frozen for decades and decades at a time. When it's frozen, it's completely biologically inactive. No microbes are doing their thing in there. It's stable. Now, soil, you guys probably have heard, stores a lot of carbon, right? Stores a lot of dead material. So these soils are great for helping with climate change. However, as the temperature rises, we're actually starting to see more and more of that permafrost soil start to thaw. So as that soil starts to thaw, the microbes in the soil wake up. And those microbes, as they wake up, just go about doing their business. They start eating all the dead material that soil stores, these permanent frozen soil store. As they do that, they produce lots of CO2. And more importantly, they actually produce a lot of methane. Those are both greenhouse gases. So as more and more of permafrost melts, we produce more and more CO2 and methane in the Arctic, which contributes to rising global temperatures, which leads to more permafrost thawing, which leads to more gases, which leads to higher temperatures. So we have this really, really awful feedback loop where more temperatures leads to more gases, which leads to more temperature, which leads to more gases, and it just feeds into itself over and over again. So again, it's this really, really awful cycle. And you can sort of see this here. So we have this lake here, or I should say this little pond here, it's frozen. And you can see these little gas bubbles all around this pond. It looks pretty cool. But what's actually happening here is that the permanently frozen soil under here is actually thawed under this little lake here. It's thawed, and the microbes are producing lots of these gases. And you can see all this gas bubbling up and getting trapped in the sea, in this ice here. And so, as I mentioned, this climate feedback loop, very much like this climate feedback loop, makes climate change worse. But while we understand this one very, very well, this one is actually just a giant black box. We actually don't know what the heck is going to happen with this going forward. Why is that? Well, there's two reasons. A, it's really hard to study the Arctic. Not a lot of people want to do it. It's also really hard to get to places like this, right? The Arctic is tough. But it's also really hard to understand soil. Soil is really hard to understand. And so both of those avenues make this feedback loop very, very difficult to predict. And if climate change gets really, really bad in the future, it's probably because of this feedback loop. Because again, it's really hard to understand and it's really hard to predict. So those are our feedback loops. But let's talk about the economic effects of climate change. I've sort of been alluding to this over time as the sort of lecture has gone, but climate change is projected to impact economic functionality, I guess, globally. So the costs of climate change are expected to be, at the bare minimum, 5 trillion by 2100, but some estimates put it close to 100 trillion by 2100. So the global GDP, as you guys probably remember, is close to 120 trillion in that ballpark. So you're talking about huge sums of money here, right? Massive, massive amounts of our global GDP. 5 to 20% is what it's projected, because the global GDP should rise by 2100, of course. Now, let's sort of think about that, right? What are the sort of costs that go into that? Well, we sort of talked about the effects of air pollution on lost work days, and that affects the GDP. But the other part of climate change is, well, what does extreme heat waves do, right, to our infrastructure? What does rising seas do to our infrastructure? What does more harsher storms do to our infrastructure? All of that costs money to fix, both from the private sector as well as from the government level. And I like this quote from the Office of Government Accountability, and they say climate change has cost the United States taxpayers more than $350 billion over the past decade. And according to the report released last year from this office, by 2050, that figure will be about $35 billion per year. Costs include cleanup, disaster assistance from flooding and storms, which are set to increase under rising seas. So this nice little quote from Market Watch. I'm sure you guys probably heard of Market Watch at some point, but climate change is expected to have some pretty dire effects on the economy. And so you can read a little bit more about this. This is from Columbia University. It's a pretty good look at it. But the reality is climate change is expected to cost a lot. But let's put this in context of what it would cost to fix climate change. And when scientists and economists get together and they start to say, okay, what would it cost to reduce greenhouse gas? They actually come to the conclusion it would cost less than 1% of the annual GDP to fix our greenhouse gas problem. And when economists start to analyze how this will affect job growth, the economy, most economists, about 65% of them, come to the conclusion that climate change and addressing climate change will create far more jobs, create much better and much more sustained economic growth than sort of not addressing it, right? It's not, so climate change, fixing the problem will hurt the GDP, will hurt our economies far more than simply addressing it. So you can take a peek at that here. Really cool study about the effects of not addressing climate change versus the cost of addressing climate change. So the economy is one thing, but real estate is also impacted by climate change. And it's not just like real estate. So this, I like this graph from the New York Times that I pulled a few years ago, where it looked at the declining costs of property value all along the eastern seaboard from New Jersey all the way up to Gloucester and Salisbury, Massachusetts. We're thinking about these low-lying areas where people like to go vacation, right? Tourism. We're also thinking about people's homes, right? The value of your home actually under future climate change might decrease depending on how close you are to the ocean. And that's just housing, but it's also infrastructure, right? There's also effects on our agriculture. And there's also effects on the financial market. And that's not just like the cost of house or any of the things we've talked about thus far, but it's also things like, how does it affect price, the certainty of a price, right? How does this affect supply chains? How does it affect the production of raw goods? How does this affect the insurance industry? How does this affect your equipment, right? What does this mean for things such as stranded assets due to climate change, right? Assets you can't get at because climate change has made it impossible to get at. So there's lots and lots of economic effects of climate change. It's not just an environmental thing. As we discussed, the environment is directly tied to what humans do, right? That $100 trillion value to us is at threat because of climate change. But despite all the stuff we've talked about today, there's overwhelming evidence that climate change is real, and the effects that we're going to see are, well, real. Sort of no other word I can use to describe that. Climate change is a really consensus thing. That level of certainty, again, is like on the borderline of smoking causes cancer certainty. So 98% of all scientific papers on climate change show that climate change is real and man-made. So when we have that level of certainty in the scientific community across hundreds of thousands of published research papers, climate change doesn't have a debate. There's no debate on climate change in the scientific community. The only time a debate rises in the scientific community is when unethical science is done. So we can ask the question, why is there a debate in society? And why is there a political debate around this? Not just here, but also places like Australia and China and the EU. Why is there still a debate? Well, as with most problems, and we saw this pretty easily with COVID, the scientific debates that didn't exist, the same one as with COVID really, became a political identity, right? Climate change denial is an identity, right? And sort of not just a political, but also an individual philosophy. And so these things pop up. And you might ask yourself, well, how does this pop up? And the answer is actually pretty clear. The sort of the biggest fuel to the fire of climate denial actually came from the fossil fuel industry. Why is that? Well, the fossil fuel industry is the one who's selling fossil fuels, right? That contribute to climate change. And it is in their best interest as a business to keep climate change essentially on the back burner, right? So they can sell as much of their plastic, sell as much of their petroleum as they physically can before before we put a ban on it, right? And so if you want to read a little bit about this article from the Conversation is a pretty good look at the disinformation campaign by the fossil fuel industry. But it's not just the fossil fuel industry, it is a political belief. People do strongly believe climate change is a hoax, despite the incontrovertible proof of climate change. And you can see this across the political spectrum, whether it's former presidents, current senators. Everyone has an opinion, some way, shape, or form, but you also see it across the private sector. And I love this quote from Stephen Colbert that I think it's really funny, but maybe you won't find it funny. Colbert says, "Global warming isn't real because I was cold today. Also great news, world hunger is over because I just ate." Right? And it really highlights the matter of that climate change, while it's a certainty, really picks up a personal identity to it. So again, it is a personal matter, but it's really not up for debate at this point. It is a certainty among the scientific community. And regardless of what anyone tells you, climate change is real. And you could see the global markets, you can see the global institutions actually starting to prepare for it. We're seeing more and more business divesting from fossil fuel companies, whether it's companies, universities, and churches, or if it's even, say, large governmental bodies such as like Denmark and Sweden. They're completely divested from fossil fuel industries. We're seeing insurance companies recognizing the risks climate change poses now and in the future to their profits, right? Because they know it's coming. We're also seeing business invest in more environmentally sustainable practices, again, to try to fight climate change. And we're also seeing climate change is a national security issue. When you sort of read about the Army and the National Guard and all the military branches' thoughts on climate change, they don't deny it. They recognize it as a matter of national security. And there's been some evidence, not some evidence, a lot of evidence suggests that the civil war in Syria actually is partly to blame on climate change and some of the effects of climate change. So climate change is a matter of perspective, but there is a level of certainty about it. It's not really up for debate as much as people would like to debate it, but it still is in the public sector, unfortunately. So climate change, it's projected to hit everything. And that's why at the beginning of the class, I told you, like, this is the issue of this semester. It really is. It affects everything. Now, climate change also poses a moral issue. Now, we're going to talk a little bit about environmental justice at the end of the semester, but the reality of climate change is that the people that are most likely to suffer from climate change are actually already the poorest people on the planet, which is an awful thing, right? We think about the people that cause the most harm of climate, the larger nations, the most polluting nations. They're less likely to see the effects of climate change, but some of the poorest areas are likely to see some of the most damaging effects of climate change, which is really, really unfortunate. They're already doing poorly. We're kicking them essentially with climate change when they're down. And then the other thing is actually this intergenerational equality. There's a huge burden on us, on your generation and my generation. This problem was created by my parents' generation and probably your parents' generation as well. And the people that have to pay the bill that our parents put forth is us and our children. All right, so there is an intergenerational equality problem here as well. We didn't really create the problem, but we have to pay the bill on the problem, which is kind of unfortunate. So this brings us to our sort of final notes on the day. What can you do? The reality is you could do lots of things, right? You can get your energy. So for instance, like I get all my energy from wind and solar power for my house, right? I still drive a fossil fuel car, but eventually I'll switch to an electric vehicle. I try to walk and bike when I can. So there are choices you can make, right? Wasting less food, things like that. You can offset carbon, so you can donate to things that help plant trees and stuff like that. You can also donate to scientific institutes to help research and try to offset things. So there's lots of things you individually can do, but while you have some power as a consumer, the burden of this actually is at the policy level. That meaningful change to climate change is not going to be done through you and I. It has to come through large systematic changes, right? That's the reality of it. We can't fix billions of tons of CO2 going into the atmosphere by all of us deciding, oh, I'm going to not eat meat anymore, right? There's lots, that's just not the way it works, right? You can't, you as an individual can't swallow a whale, so to speak, right? Large policy measures needs to be taken. And the reality is, we actually start to look at the CO2 budgets of like where most pollution comes from. About 70% of the world's greenhouse gases can actually be traced to 100 single companies. And while we are the ones consuming the things, the reality is that we could solve climate change by making a very small amount of companies essentially fix their climate causing problems, right? And you can think whatever you'd like about that statement, but that's the reality of it. The individual, as we'll talk about with trash, can't make a big difference. The burden is on the mega polluters, right? The Exxon Mobils of the world, the Amazons of the world, right? These places that have huge carbon footprints. And the other thing I'll just make mention of is when you look at people like, say, Bill Gates, really, really wealthy people have a much larger carbon footprint than we do. Bill Gates has a carbon footprint about 1,000 times bigger than about 30 times bigger than you or I's footprint. So large companies pollute a lot, and we could do something about that through policy, as does as does, say, restrictions on and sort of trying to keep the wealthy from overindulging. So there's lots that can be done, but again, it's such a gargantuan problem. And the Paris Climate Accord was great, but we have to adhere to the things we set. We have to make large systematic changes. So what are our conclusions from today? Well, temperatures are higher than in the past 1,000 years. There's no debate on climate change. We need to reduce emissions. Now, we're really looking to face some pretty severe economic, environmental, and social problems down the road. And there is, as I said, there's no debate. This is caused by humans. And it really is an all hands on deck problem to solve climate issues as a whole. And I'd like to sort of give you a note. So a couple of years ago, I was at a conference and I heard this really great speaker. I can't even remember who it is at this point. And he gave this really powerful speech at the time. It was to a bunch of scientists. So we all knew what was going on with climate change, but I remember just being so impressed by this speech. I had to ask the guy for his speech. So he sent me a speech. And so I'd like to read part of his speech because, again, it was so powerful to me as a person at the time. So let's dive into it. It's a couple slides. So we is the root of the problem. Humanity has to create by degrees a Gordian knot of incentives that no one person or even country has the ability to cut through. It is no one individual or country. It is a system. No one governs the system. It is governed by webs of incentives acting across individuals, nations, and corporations with reward and have normalized the very actions that will accelerate the process of climate destruction. Every single person's standard of living in developed nations is built on the status quo that is ruining the planet. Elected leaders don't want to upset the status quo for fear of being ousted by the people. The people are either brainwashed by corporations into believing there is no problem or otherwise pissed at corporations but relatively helpless to do anything about it. No one leader or corporation is going to do the selfless thing. It's a tragedy of the commons situation. They all take advantage of the situation because everyone else is. Every country worries that if they reduce emissions, they have no guarantee that any other country will. No one country will make a difference alone. There's no guarantee that another country won't simply increase their emissions and gain economic or military advantage over their rival. Every world leader, corporation, executive, and billionaire knows beyond a shadow of a doubt that climate change is real and that we are causing it. They know, but everyone is paralyzed by the tragedy of the commons. Major corporations and countries of the world are paralyzed by one another and by their own populations who are addicted to a way of life that is not sustainable. Any individual who is 30 years old now, living in a developed nation, could conceivably live a relatively normal life from now until death. Climate change will continue to accelerate and billions will suffer and die, but they may not be able to live relatively comfortable lives. We won't start to see the really horrific shit, his words, not mine, until maybe 2050. So it'll be 60 before they truly apocalyptic stuff like global inescapable heat waves start. And maybe by that time we'll have underground cities that people have adjusted to where they can live with family and friends in some sort of ordinary life, not their ideal future, but a future. This is the calculation they're all running in their minds. Why should I forsake a normal life, they ask themselves, and live in a hut in the woods when doing so won't make a difference and will only deprive me of a chance at a normal life, especially when I wasn't even responsible for this mess in the first place? Why should I stop traveling and spending and forsake the pleasure of the earth as it is now, especially given the likelihood that each year that passes, it will be less habitable and less paradisical as it is now? Across every developed nation, people are running this calculus through their minds. Even those accepted climate change is real and truly want to do something, but have given into a sense of helplessness and the inability to ability to affect change and surrender to a sense of inevitability of the coming climate devastation. The attitude across people's will make it much more difficult for any politicians who are calling for widespread sacrifice of commercial goods and progress into scaling emission-causing industries and potentially temporarily or permanently displacing labor forces there. Because if you've already accepted the inevitability of climate change, and if your mind is already accepting the level of survivability that you're willing to accept in the inevitable future, why would you sacrifice your best years now for the ambitions of politicians whose plan no one even has any confidence will affect change anyways? That's the other irony. The more real climate change becomes gradually, the less willing people will be to sacrifice their last chances at a normal comfortable life, not just for themselves, but for their family, for their understanding of the world and their place in it. That's the issue of our current situation. Consensus appears impossible. Every individual is doing what's best for themselves, even knowing that is a detriment to the world. Because in isolation, their bad thing doesn't make a difference. So they do the bad thing, and everyone does the bad thing. And as the population keeps changing, the calculations per individual doesn't change, but the damage of the aggregate continually increases. It will take a wide-scale planetary devastation on the magnitude of COVID. I added that part. It was a different disease at the time. I added COVID as a note, but of longer duration to actually produce enough unified consensus to take action. But by the time we reach that point in earnest, it will be too late to do anything but endure the climate apocalypse for the next 50,000 years. The biggest problem with climate change is that it will not just suddenly become devastating immediately, like if we discovered a world-ending comet a week away from striking Earth. If climate change did present this sort of immediate, dramatic, cohesive threat, that would actually be beneficial to us because the human race is actually good at organizing quickly and uniformly around immediate, urgent, emergent, unified threat. The reality is things will get a little worse each year, little by little, in increments that allow everyone to adjust to the new normal year after year in isolation. The mass displacement of human bodies by the billions as third world countries collapse under climate devastation will be met with increased hostility by developed nations and will increase the clout and power from myopic fascist regimes that will exploit the situation for power, which will undeniably hamstring any action on climate change in the inverse correlation to the level of, oops, I can't believe I hit that. Sorry about that. I hit my thing, which will undeniably hamstring any action on climate change in inverse correlation to the level of consequences from climate change. In other words, the worse climate change gets, the more the world will react in ways that further preventing us from taking action to mitigate climate change. So I hope I'm wrong. I'm going to continue to act as though I'm wrong and promote awareness and donate to climate groups and boycott polluters. This is a very bad situation with no clear and easy way out. Now, is there hope? There is always hope, always. What shape it will take, who can say? What can be said is that even with the possibility of hope is it asymptomatic to zero, there's never a cause to act without hope. You play the game until the last moment, because even if the victory is slim, it's guaranteed if you stop playing the game. Norman Borlaug, which I linked here if you want to read about him, is a name that we don't hear often, which is kind of funny because Borlaug actually saved potentially billions of lives. Around 100 years ago, Norman invented a species of high-wheeled wheat that gave countries with little access to food availability to suddenly produce enough wheat to save billions by death from starvation. Who could you be? You don't need to be any sort of genius to potentially create by design or by accident something that changes the course of history. Because I articulate the problem, people ask me for the solution. I don't know the solution, but you might, more accurately, all of us do. In our collective imagination is the capacity to bend the universe itself. I can't fathom what that solution will look like, but maybe you don't, and maybe you don't find the solution, but maybe you, in your efforts and unknown to you, inspire ones that do. The sun is low, the time is short, the cataclysm is here, darkness surrounds. But life was born in primordial earth of fire and lightning and endless turmoil. And in that chaos, life was born. And so as long as we exist, their hope exists. And I don't know. I know that was long, but I thought it bared sort of reading to you guys because it really hits all the points we talked about today. And that climate change can seem like this monster thing, can seem like this untackable problem, but it's not. And humans aren't inherently selfish. We're just not as a species. We are very altruistic. And so climate change, it seems like a problem that's not going to go away. It seems like a problem that's going to get worse, but it's a problem we can fix. Look at COVID. Look how we responded to COVID, right? We came up with a vaccine in 8 months. That shit was crazy. Sorry, I don't know any other way to say it, but that's crazy. And climate is the same way. So I left this last slide here, a bunch of different stuff about acting. Right, some cool links for you guys to take a peek at if you feel like it. But things from economics to carbon taxations and all this stuff, lobbying as well. So I'll leave this for you guys to take a peek at on Blackboard. I think actually I have to update the PDF on Blackboard, so I will do that. But that's going to be the end of today's class. I know that was a lot of stuff. I know it was, but climate change is that important of a topic. Right. I hope I've sort of shown you the wide-reaching effects climate change will have, not just your life, but everyone's life around the planet. So I'm going to stop recording now.